I just realized someone actually needs to look at the YouTube account. Otherwise, if it's listed as private, we can't really see it anyways.
Yeah.
So we do need to make it public. Huh. How do I go live with this? Why is it so hard to see? It's just prepping forever. Oh wait. Oh, we already started streaming.
Yeah, strange.
Oh, we just gotta wait a bit.
Yeah.
Yeah, let's hope this works. I didn't wake up for nothing, right?
Surely it'll work.
Yeah.
Surely.
So did you actually fall asleep, Ahmed, during that audio call?
I don't remember hopping off the call.
Yeah, cause everyone else was like, oh, he might be locked in, and then we just left, and then you're still in there, which was very impressive.
I don't remember hopping. I can't fall asleep.
Lol. Hey, this is a bit worrisome.
Why is it taking so long? It wasn't.
Yeah, it's a bit worrisome, isn't it?
I mean, the signal in this room is not bad, right? It's just.
It says excellent. So I'm going to assume it's not bad. How about we make a public one? Surely no one's watching at this point.
Yeah, I mean, it's like no big deal, right?
Yes, it's not a big deal.
We're not really doing anything anyway.
Yeah, they don't really care.
Yeah.
Oh, wait. Maybe we go back to see this. No, it doesn't work. Huh.
Wait, I mean,
okay.
we didn't press start streaming on the other one though, did we?
We did. I did. I
you
started
did?
streaming. 11:50 yet? It's not 11:50 yet.
No.
11:50 yet? It's not 11:50 yet.
No.
Maybe he will start streaming once 11:50 is.
Maybe. That's so weird.
Yeah, maybe we just gotta wait. This is very weird. How about we test out the writing for the time being?
I mean, it's like fine.
What time is it?
It's like 11:50.
Oh, okay. Well, wait. There is a bit of a delay.
Yeah.
I mean, we can wait until 11:51. If nothing happens, that means there's a bit of an issue.
Yeah.
Let's go back to OBS. What does that look like? Everything is set up.
It doesn't. Everything looks right.
Can you test? Oh, the audio is also working. And you might have to speak a little louder into this.
Right.
Because let's try.
Does this
you
mic
might
not
have
work?
Hello.
Yeah, it works.
Okay.
You can just speak.
We were
into
just
that.
speaking to this.
Yeah, and then like face
Face
the
that while
laptop.
doing
Yeah.
it.
Is it showing on YouTube? It's still not showing. Let me check on my phone to see if there's anything.
Yeah, that's a bit worrying.
Can you see?
Wait, can you check on your phone maybe?
Is it showing anything? It's not.
The stream.
Yeah.
Yeah, stream is just saying live in 8 minutes 30 seconds.
Oh, it's because we have another stream. You're not watching the right one. We just scheduled another one.
Yeah, this
at
is like
11:50.
11:50.
But that's okay.
If no one shows up IRL, it's like it should be okay, right?
Yeah, true.
Yeah, that's true, But
But most people that want to watch online are not trying to watch it live, right?
Yeah. I mean, if you watch it live, what's the point of watching it online again?
yeah.
Oh,
Hi.
Big goal.
We have like a bit of a problem.
It's minor issue.
Well, I've forgotten everything from the first half of this course.
No way. Nah, you'll be
Came to
fine.
the right place.
What's up?
Oh, this is
Oh,
not
wait, I saw you the other day, right? I'm Jenny. Hi, Jenny.
Hi, Marcel.
Hey, what's your name?
Oh, I'm Yui.
Yui. Hi, Yui.
Yeah. Hi, nice to meet you.
I'm Marcel. Are you doing the first part of this?
Yeah, first part. Well, second half of this.
Damn.
First part.
Could not be me, bro.
Wait, is it because we scheduled it at 12 instead of 11?
But this one is the other one, and it's public.
My other
Oh
courses-
yeah, but it's not showing.
Why does it say one viewers?
No,
Because
right.
but someone is
Someone's
waiting.
just
For
waiting.
like,
But it's just not coming up.
yeah, but I can't find it on the
Oh, wait.
because they're both
strange.
listed for 12.
Huh?
Oh, what? But this one's like
What's that?
11:50.
Yeah, which is very
That's
interesting.
Yeah.
Oh, maybe we can assume it will go live at 12. Wait,
Hopefully.
let's see. What does the stream keeper do?
I
did you enroll to?
Hello.
Oh, hi, it's actually just gonna be MathSoc.
Wait,
Right, analytics.
it's
No,
like
that's the
that
amount of
almost
people.
beginning.
Is this the behind the scenes content?
Yeah.
Yes, sir.
Just trying to get it to work.
What's your
Okay,
first
let's
one?
edit this.
Wednesday next week. That's the financial maths one.
Yeah, it's
And this
11:50
one on Friday.
a.m.
Let's
And then the other one
make
on
it
Friday.
Let's make it earlier.
Tuesday, Friday.
11:55.
That's not bad. It's better than mine.
Sorry.
Yeah, all good, all
Wait.
good.
Because you have
Okay.
like another
Okay.
day to prepare for this.
Same.
Yeah, but I have one less day to prepare for the first one.
Shit. Which one is that one?
Computing.
Oh shit, that's a bad one.
Yeah. Apparently the lecturer is too lazy to switch up the questions.
Oh, that's good.
Math2111.
Jet lagged.
Jet lag? Where were you?
Oh, where did you go?
Huh?
Where did you go?
As of 4 a.m. this morning, Sydney time, I was in Queenstown, Singapore.
Oh,
Oh,
yeah.
dang.
I love
I did not know this.
What were you doing in Queenstown? What'd you go to?
Family holiday.
Family holiday?
Yeah.
Like a
And
weekend
I'm on a
trip.
flight back tonight.
Huh?
I on flight back.
It still shows only 2 is upcoming and both are
Were you
scheduled
going
at
against
12.
No
So
way.
my
For some
family's
reason.
like my mom, my aunt, and
Oh,
my
that's
uncle,
annoying.
They have like
Okay,
a holiday.
maybe we
They're
stop
like-
streaming
Maybe
for
we
a sec.
we get rid of one of them. So
Yeah. Just get rid of one of the testing ones. Let's just go back.
Did I just go
I was
back?
like, I can come along, except for
Um,
this
Yeah,
one
let's just go
of,
back
like,
and then
a line that I
this is
have,
listed
like,
privately.
today. So this
Oh,
morning-
is
Oh
it 'cause
wait,
that
it was
listed
private the entire
private?
time.
And then-
Wait.
Wait, so you can
Oh, but you should still be able to
Oh
see
my
your
God.
own
My
screen.
flight
Like,
time is
oh, let's
Yeah.
not make it public.
Okay.
Wow.
I would not do that. That's
Should we just
crazy.
get rid of that because
Like, surely I can arrive an hour before my flight and go through customs and board the flight, right?
I would not do that.
Still
Yes, sir.
I would not do that.
It's so fast.
So are you still like sitting? Are you still gonna like sit exams or special ones?
Yeah, I come back.
Wait, it says
on
stream
next
key is
Monday,
currently
and then both of my
assigned.
exams are Friday.
Next week, Wednesday? Oh, that's something like. Are you studying in New Zealand? Like preparing for your exams?
Nah, when you're in Queenstown.
Hold up. Let me change the stream key.
When like the chilling in the
Actually, do I need to? Oh, I don't need to.
Really
Wonderful.
Oh, nice.
It's working. Okay.
okay,
I
nice.
Good luck,
want to,
good luck.
but then no one else wants to.
What's the name of the mountain again? Remarkables. Like were you skydiving over Remarkables? Oh my
I
goodness.
want to, but
Wait,
like,
go ski.
huh?
Go ski.
I want so we're leaving Queenstown tomorrow morning.
Oh, wait,
It's like road trippy.
You surround the island.
We're gonna end up in Christchurch.
Yeah.
And then just face it out and then try to capture yourself.
Let's go do that.
Oh,
Yeah.
Right, you go like north. We went Auckland first.
I'm sure
Auckland to Sydney.
the problem is that like I can't go skydiving because like there's no one else to do it.
Oh, you remember to go through the QR code. You already pasted it.
Yeah. I put out the beginning.
Nice.
What? It's actually just a hole. It's so bad. I hate Auckland. And
Wait, is Google Meet
like
usually
for the
the
longest
same?
time, that's my only impression of New Zealand. Like I've only been to
Is it
New
usually
Zealand
the
once, and I
same?
went to Auckland.
It's like
And then you went south.
Right, yeah,
And then you
now
went-
now
There's like
south,
lag.
yeah, it's all actually
Oh,
New
lag?
Zealand.
Yeah.
There's a slight small lag, but it's very
This is
unnoticeable.
the
Should be
photo
fine.
I sent
Yeah.
everyone. Like this is
Damn, where's this?
like
Wait, what is this?
Oh, you can also minimize your screen, I think. Just
Oh, I
Oh, is it that one town next to Queenstown?
How do I?
Is that one? Is it Arizona?
how do you minimize on that is a good
West.
question.
Wait, never mind. I thought it was east.
Let me pull up my Queenstown photo.
Oh, that's good.
Do
That's
some
good enough.
geoguessing.
Wait,
I'm
full
pulling up
screen.
on that.
like
Wait, show me.
this doesn't look that big, right? But then if I zoom in,
Then
you see
minimize.
these trees?
Yes.
These
Okay,
trees are
okay,
like 25
nice.
meters.
Okay.
This is west of. This is not west of Queenstown.
Slightly big. I swear it's like
Nah, that's east of Queenstown.
north, east, southwest. It's west.
How does this work?
Okay.
That's around Arizona.
I mean, it's like there's like a bit of a lag. But yeah.
I'm like,
That should
oh,
be
maybe
fine.
it's this.
It's like very laggy though.
Yeah, we can go
Hey guys, welcome to the 2111 revision seminar. Before we get started, can I just get you guys to scan the QR code? It's like really bad.
Every once in a while. Now I work on laptop. Do you mind just quickly checking which one this is selected as? Stream settings.
Private.
Which one? Oh,
Oh my
just
gosh.
make it
Okay,
yeah,
let's make it public.
Yeah.
I'm just gonna edit it here.
Done.
Done. Save. Is that all?
Nice. You should work in a while. Should work in a while. We don't need to like cap it. It's fine.
Yeah, for those who just arrived, can you just fill the form on the QR code? Thanks. Okay, for those who just arrived, can you just fill out the form on the QR code? Thanks. Yeah, just on my laptop. Should be. Yeah. Yeah. Yeah, it's coming right. a moment.
Wait, why do you use the laptop, the desktop computer?
Because you just somehow wanted to use it.
What? I literally set it up.
No, it's fine, it's fine. Is it working? Otherwise we can live with a bit of that.
Yeah.
Try to speak as loudly as possible.
Yeah, just put it there.
Yes.
Should be fine.
Yeah, I'll check the stream. You guys can continue, right? Oh, math is hard. Is your pen about about 1 minute?
It's fine, we have like plenty of hours.
Yeah. Actually, this is for us to look at, right? Like this one.
Yeah. Wait.
That won't be streamed.
Oh, that's so much better.
Oh, that's big.
That is so much smoother. Is it? Yeah, that's
Yeah,
better.
maybe it's not for your screen.
Yeah, it's just the room. Yeah.
So all of that.
The room is just bad signal.
Yeah, it's okay. So
Ah,
you
it's
guys
okay.
can
This is
still,
fine.
yeah. Maybe you could go back to the meeting later when it drops out.
Yeah. Okay.
Alright.
Can I introduce the topics? Like
Yeah,
when
sure.
you go to that slide.
It's just,
Wait, one second.
it's irrelevant. I mean, that's not a part
Yeah,
of.
that's just for
We
us
can
to
just
look
go
at.
off.
Yeah.
We can just go using this instead.
Wait, do you want to do this first slide? Just introduce the topics. Say like I'm doing 6.
Yeah.
This fine.
Okay, hi guys. Welcome to the seminar again. For those who just walked in, can you just scan this QR code? Sorry, give me a second. Okay, that's better. Yeah, so as I was saying, for those who just joined us, can you just scan that QR code and fill out the form? And yeah, we can just skip this. Okay, so for part 1, we're going to go through these topics. Yeah, what's that? Oh my gosh. Okay, guys, sorry about that. Just give us a few seconds.
Or a few minutes.
Yeah. You know, let's just go back to this. Let's just go back to this. Okay. Let's get rid of that. I mean, I'll just.
Can you minimize this?
It's fine. Slide to a side. Okay. Okay. Back to this. As I was saying, for part 1, we're just going to go through these topics. So Sading here would go through topics 1 to 5, and I would go through topics 6 to 10. I'll pass it over.
Okay, curves and surfaces first. So this is a pretty chill topic. We're just going to define what a curve is. So a curve is a function which takes in a real number on an interval and outputs a vector. So for example, you might have something like c of t equals like t squared. Takes in a real number t and outputs a vector in terms of t. So this is pretty chill, right? Like, I don't need to go on too deep into this. A multiple point is a point where the curve passes through it more than once. So basically, for example, like c of t1 equals c of t2. So that means there's 2 different values of t for which the curve achieves this value. So it's a multiple point. And a curve is closed if its endpoints are, the values at the endpoints are equal. Okay, now just some basic limits and calculus. So if you want to take the limit of a curve, it's really easy. You just take the limits of each component. So like the limit as t goes to 1 of say like t squared, it's just like 1 and 1. Okay, that's a terrible example, but you get the idea. You just take the limit of each component. So the limit of t and the limit of t squared. And it works the same for derivatives. So as long as the derivatives of each component exist, then the derivative of the curve exists. An important geometric interpretation for curves is the tangent vector. So c prime of t is basically the tangent vector at the point t. You can also interpret it as the velocity at t, and its magnitude would be the speed at t. And c double prime is the acceleration. So this is kind of like a physical interpretation. Okay, surfaces. So you guys are used to this, right? We've got graphs. You got implicitly defined surfaces. So something like f of x, y, z equals 0. Then you've got parametrically defined surfaces or curves. So here we have this is a circle centered at AB and with radius r. Okay, we're just going to do a pretty chill question. This would appear early in the exam. This one here is from question 1 of 2022 final exam. So basically, we're just going to try to graph this region. So it's the set of all, okay, I probably should say set of all x, y, such that this is satisfied. Now, if you want to graph this, this is kind of like like conics basically, you want to probably complete the square. So, wait, let me get this. Okay, I'll just do it. So you have 4x squared minus 8x minus y squared minus 4y less than equal to minus 4. Now if you want to complete the square here, we can write this as 4x squared minus 2x and then minus, I'll just say y squared plus 4y. Now complete the square with the x, you get 4x minus 1 squared, and then a plus, minus 1, and then minus, I guess, y plus 2 squared, and then minus 4, but then it becomes a plus 4. And then basically, you can see these are going to cancel the 4 and minus 4 here. So you're left with 4x minus 1 squared minus y plus 2 squared less than equal to minus 4. And then I guess we can divide by 4 in the inequality. X minus 1 squared minus y plus 2 over 2 squared. I put the 2 inside the square. Less than equal to minus 1. Oh, sorry. Then you have y plus 2 over 2 squared minus x minus 1 squared. And then I'll just say the actual equation of the, I guess, the curve, and then we'll do the inequality. So it'd be something like this. Now, if you want to graph this, you might need to revise your like conic sections and stuff. But basically, this is going to be centered at x equals 1 and y equals minus 2. And then it looks something like this. And now for the region, you can test a point basically. So I'll go back to the original. I guess we should probably check what the y-intercepts and the x-intercepts are. So if you go here, the x-intercept is when y is 0. So that would be 4 minus x minus 1 squared equals 1. And then x minus 1 squared equals 3. So x equals 1 plus minus root 3. So I guess a 1 plus root 3 here, a 1 minus root 3. The y-intercept is when x would be 0. So you have y plus 2 squared over 4 minus 1 equals 1. So y plus 2 squared over 4 equals 2. Wait. So y plus 2 over 2 squared, equals 2. Y plus 2 squared equals 8. And then y plus 2 equals plus minus, I guess, 2 root 2. And then you can go from there. But just to graph the inequality, we can sub in a point to figure out which side the region is. So we can sub in, say, like 1, 0. And that would give, in the original one, actually I'll just look at the curve here. If you sub x equals 1 and y equals 0, you get 4 minus 1, which is 3. And that would be, that would actually be greater than or equal to. So you get this region here. So yeah, just revise your graphing of like these sort of, this is hyperbola. And yeah, this is pretty chill. Okay, finally to some more interesting topics. We've got metrics and sequences. So you guys know a metric is like a distance function. It takes in 2 vectors and outputs a real number, which basically measures the distance between the 2 vectors. So you need 3 properties or 3 conditions for something to be a metric. First of all, it has to be positive definite. So like that just means the distance can't be negative. That's like pretty intuitive. And then also it has to be definite. So that means the distance is 0 only when the points are the same. And then symmetry, the distance doesn't matter which way you measure it, it's equal. And then triangle inequality, it's like the distance from x to y is shorter than the distance if you go through an intermediate point z, or less than equal to. Then convergent and Cauchy sequences, you guys probably used to this, but the sequence converges to x if, and then you have this epsilon delta definition. For all positive epsilon, there's some integer k, such that for all lowercase k greater than or equal to k, the distance between the sequence and the point x to which it converges is less than epsilon. For Cauchy sequences, it's a bit different. This basically means like the terms of the sequence get closer and closer to each other as you go far enough out to infinity. So for all epsilon greater than 0, there's a k such that for all j k greater than equal to k, you have this. The distance is less than epsilon between xk and xj. Now something important to note is if a sequence is convergent, then it's Cauchy. But the other way isn't necessarily true for arbitrary metrics. You need something like the Euclidean metric for that to happen. In that case, they're equivalent. Okay, here's like a more intuitive sort of interpretation of them. You can say a sequence converges to x if the limit of the distance goes to 0. And by that I mean like for all epsilon greater than 0, there exists a k, positive integer k, such that for all k greater than k, you have this thing less than epsilon. But this is useful because if you don't want to do it directly by epsilon delta, like if you just want to gain some intuition for the function, you can basically treat it like a normal limit. We're going to use this in a few examples later on. And for Cauchy, you can kind of think of it like this. This is more like an intuitive way to think about what convergence and Cauchy sequences mean. Okay, so there's also something about convergence of components. This is similar to the thing for curves, but basically a sequence converges if and only if the components of it converge, where it's a sequence of vectors basically. Okay, now let's get into a bit of a crazy example. We've got this weird metric here, delta, and we have this sequence xn. So first of all, we want to prove delta is a metric. So you just need to show it satisfies those three properties. First of all, like positive definite. Well, this thing is always positive, right? It's just the absolute value of some real numbers. So it's definitely non-negative, I guess. Now, is it definite? So that means the distance is 0 if and only if the points are the same. So if x equals y here, you can clearly see you get 0, right? Because this is just going to be x and this is x, and they cancel out. So that means delta of x is 0. But now we need to prove that if the distance is 0, then x and y are the same. So we'll just suppose the distance is 0. Then what does that mean? Well, it means this absolute value is 0, so it means this is equal to this basically. So x on 1 plus max 1x, I guess, equals y over 1 plus max 1y. Now, how do we prove these? This means that x equals y. Well, you can kind of think of this as like a function, right? Like, if I define phi of t to be say t over 1 plus max 1 and absolute t, then if we can prove this function is 1 to 1, then it would mean that whenever phi of x equals phi of y, then that means x equals y, right? So you can do this a few ways. You can do it by, I guess, it's like a bit piecewise function kind of. You can kind of graph it if you need to. So you just take cases when absolute t is greater than or equal to 1 or not. Let's go back to the original. So if absolute t is greater than or equal to 1, then the max of 1 and absolute t would be absolute t, right? So you'll get basically, okay, I think I'll rub this out. So you can write this as a piecewise function, phi of t equals t over 1 plus t if, say, t is greater than 1. So t is greater than 1 also means absolute value t is greater than 1. So this would work. And then if t is less than 1 or less than minus 1, then absolute t is still greater than 1, but here you'll get t on 1 minus t. And in the last case, when t is between minus 1 and 1, then what do we get? We get, then the maximum would be 1 here. So you get t over 1 plus 1, or I guess t over 2. Okay, that seems to be correct. Yeah, okay. Now if you want to graph this, well, for t greater than 1, this is just like a normal like hyperbola. So for t greater than 1, well, as t goes to infinity, it's going to approach 1, so I'll just draw like an asymptote here. And then at t equals 1, it's going to be 1 over 1 plus 1, which is half. And then it's going to approach like this. Now, how about for absolute t less than equal to, wait, this should be absolute t less than equal to 1. Well, in that range, it's t over 2, so it's just like a line through the origin. Guess there's a minus half here. Okay, that's a straight line, trust me. Now, for the remaining part, it's going to be t less than minus 1. So t on 1 minus t. And at minus 1, that's going to be minus 1 on 1 minus minus 1, which is minus 1, minus half. So you can see it's going to be continuous. And as t goes to negative infinity, this is going to approach minus 1. Something like this. So you can see this is going to be injective, right? It's going to be 1 to 1. And so therefore, you've proven that. So that means if these two are equal, it means x equals y. So yeah, now we need to prove the triangle inequality. But luckily, this isn't actually that bad. Normally, the triangle inequality takes more time, but not in this case. Delta of xy is absolute phi of x minus minus 5y. Now, you can just use the normal triangle inequality here for absolute value. That would be delta of xy is less than equal to absolute phi of x minus, say, phi of z plus absolute phi of y minus phi of z. This is just the normal triangle inequality for the absolute value, because that's a norm. And yeah, that proves the triangle inequality. That proves that if you have x, y, z, the distance between x and y is less than equal to the distance from x to z plus the distance from y to z. Okay, now we need to prove this is a Cauchy sequence. So first of all, what is y sub n? Well, because you have minus 1 to the 2n minus 1, that's going to be just negative 1. So this is our actual sequence here. Now, how do you prove this is Cauchy with respect to delta? Well, the trick is we're going to basically consider the term, when you're doing the epsilon delta proof, you need to consider yj minus yk, and you need to prove that's less than epsilon, right? So we're just going to focus on this term and see what we can do with it. So we just need to look at this metric. Oh, sorry, this shouldn't actually be absolute value. This should be the special metric we're doing, delta of yj and yk. So you have x over 1 plus max 1 absolute x, okay. So what is actually this? Well, it's going to be the absolute value of, first of all, yj is 1 minus 2j. So 1 minus 2j over 1 plus max 1 and 2j minus 1. So here I've taken the absolute value of 1 minus 2j. And you have something similar. So just simplifying this, you get 1 minus 2j, and 2j minus 1 is going to be bigger than 1 for large j, so that's just going to be 2j minus 1 when you take the max, and you get 2j. If you simplify this, you get 1 on 2j minus 1 on 2k. So basically, we've just found like a closed form for the distance. Now we just need to figure out how to write the proof, I guess. So just write this up here. Delta of yj and yk is absolute 1 on 2j minus 1 on 2k. Now, one thing you can do is you can basically take j less than k without loss of generality. It doesn't matter which one, because if one of them is bigger, you can just swap the order. So we're going to assume j is less than k, and then that means this is actually just positive. Okay, now we want to bound this against epsilon when we're doing an epsilon delta proof, or epsilon n k proof, whatever. So one thing you can do is, just to make an easier bound, you can say this is less than 1 on 2j. And this is like basically pretty simple trick. It's like removing a negative term with an inequality. Because this minus 1 on 2k, you're subtracting it off. So this will be less than if you didn't subtract it off. Now you just have something simpler to bound, basically. And if you want to make it even simpler, you could say this is less than 1 on j, because half is less than 1. And now all you have to do is bound this. So this is the bound we're trying to get, basically. We just need 1 on j less than epsilon, and then we can basically write the proof. So that would mean j is greater than 1 on epsilon. Okay, so now if you want to write the proof, I'll rewrite the definition of Cauchy. For all epsilon greater than 0, there exists k such that for j k greater than k, you have the delta of yj yk less than epsilon. Okay, so to structure the proof, you first take an arbitrary epsilon, so I'll just say let epsilon greater than 0. Now what k are we going to choose? Well, we wanted j greater than 1 on epsilon, so we can take k to be 1 on epsilon, but that won't work exactly because we need an integer. So one trick is you take the ceiling of it to make it an integer. And now we'll suppose basically, suppose jk greater than k. Then what do you have? Well, then you have delta of yj, yk, sorry, that should be a comma. Well, we already saw this was, I think, half j minus half k, and we'll assume here j is less than k. Then, once again, using the same bound, we can show this less than 1 on j. Now, since we assumed j is bigger than k, we have j greater than ceiling of this, so that also means j is greater than 1 on epsilon, so then this is less than epsilon. And then that basically completes the proof. Okay, now, okay, I had 2 slides for this, I did not realize. Okay, now we have a new question. Wn equals min of this, so first of all, like, we should figure out what Wn is, because this is a bit annoying form at the moment. So it's the min of minus 1 to the n and 0. So I mean, if you want to do something with this, you'll need to probably take cases for n, right? Because if n is even, n is odd. So n is even, what do you get? You get the min of n and 0. The smaller one's going to be 0. And if n is odd, the smaller one would be minus n, because you have a minus 1 to the odd power. So I guess this is what Wn is. Now, so our goal is to determine if it's Cauchy, convergent, whatever. So we'll try to prove that it's not Cauchy. So how would we prove it's not Cauchy? Well, that would just mean the distance wj, wk does not go to infinity as jk goes to infinity, like intuitively. So once again, you just always consider this term, like try to expand this term with the metric, because otherwise you can't really do anything. Now, once again, because Wn is it's piecewise, it's 0 or minus n based on the parity, we need to probably take cases again. So if j is, say, odd and k is even, we'll look at that case first. Then what does the delta of wj, wk become? Okay, let's see. So this metric is so annoying. So if j is going to be even, I think, wait, did I say j is odd? Okay, j is odd. So then I'll just write the phi again. Phi of t on 1 plus max. So I think it was this with the absolute value here. Now if we take j to be odd, then we get a minus j. So phi of j would be, phi of wj equals basically phi of minus j, so that would be minus j over 1 plus max j in 1, and that would just be this. But for wk, we get something nicer, because if k is even, then wk is 0, so then you just get 0. If you sub in phi of wk, you get 0. Because if you sub in 0 into this, you just get 0 over something, and that's going to be 0. So in this case, we have something pretty nice. We have delta of wj wk equals just the absolute value of this, which is going to be j over 1 plus j. Okay, so now we just need to think, will this actually go to infinity as j and k go to infinity? Because if it does, or if it doesn't, then that would mean it's not Cauchy for this. Now, as j goes to infinity, obviously this is going to approach 1. So basically this is not going to be Cauchy, that's the idea. But now we just need to prove it. I'll just go through a sketch of the proof. But the idea is we just need to take this case. When j is odd and k is even, that's when you get this sort of, that's when the danger happens. That's when it's not going to approach 0. So I'll just go through like a very brief sort of thing. So if you want to prove it's not Cauchy, first of all, the Cauchy definition is for all epsilon greater than 0, there exists natural number k such that jk greater than k implies distance of wj and wk less than epsilon. Now, if you want to negate this, to prove something's not Cauchy, you need to prove the negation. So for all there exists epsilon greater than 0 such that for all k, there exists jk greater than k such that this distance is always greater than or equal to epsilon. Now, what we saw was if they have opposite parity, if j is, what's even going on? Okay, so what we saw is if j is j is odd and k is even, we saw that this thing is j over 1 plus j, and that will not approach 0 as j goes to infinity. So you can just take that case. So we'll take, so if you want to construct the proof, we'll basically say that epsilon equals, well, I think we should look at this graph of j on 1 plus j. So if you have on the j-axis, so it is -1. It's for j positive though, so, and as j goes to infinity, approaches 1. So now you can see this is not going to approach 0, but after some point it's always going to be greater than or equal to half, I guess. Right? You can check specifically when that is by solving the inequality, but we won't do that right now for time constraints. So the epsilon equals half, then I guess I should have said take epsilon equals half, but it's fine. Then let k be a natural number, and we'll choose, you just need to choose j and k with the right parity, remember, because that's where the Cauchy sequence breaks down. So we choose j and k with j odd, k even, and greater than or equal to k. You can do specific examples, and you can do a specific j and k, like you can say like 2 times k plus 1, for example, if you want to do odd. But we'll just say this for now. And then, so that's the exist part. And then we've shown basically this thing becomes, you also need to make sure this j and k are such that it's after the point where this thing is greater than or equal to half. And with j on j plus 1 greater than or equal to half, and similarly for k. And then you do get this, as we showed, and this would be greater than or equal to half, which is epsilon. Okay, so that's why this is not Cauchy. Just like a quick summary of what we did. First of all, find what Wn is, because it's not really written in a useful form. Then you always consider the distance function between the wj, wk. And then you try to write that in a certain way, try to mess around with it. And you need to take cases for j and k even or odd, because this guy depends on whether n is even or odd. And you can try to see if it approaches 0 as jk go to infinity. We found a case where it didn't, so we used those parities. Okay, I'll leave this as a exercise, because I'm probably going to say that a lot today, because we have a lot of questions to get through. You guys can look at this on the recording later. Is this still a metric? Okay, I'll give you a clue. It's not a metric, and to prove it's not, you just need to prove that one of the conditions is not satisfied for a metric. So maybe delta of like the same point AA is not 0 for some A. So it's not that hard. You can actually have a go at this later. And then another practice question, show that every Cauchy sequence of real numbers is bounded. So if you've seen the proof that every convergent sequence of real numbers is bounded, it's kind of similar. You just need to prove it's eventually bounded. So like imagine I have a sequence like this or something. You just need to prove it's eventually bounded, and then the remaining part is finite, so then that part will be bounded. But that's just an idea for the proof. You guys can try this later on in your own time. And another practice question, this one's a bit difficult. Prove from definition that this sequence is Cauchy. So it's a bit weird. It's like if n is a power of 2, then it's 1 on log of m, and it's 0 otherwise. And if you want to look at the proof later just to check your solution, it's here, but I won't go through it because it's a practice question. I said it doesn't go infinity. Oh, sorry, you're right. Yeah. Okay, guys, we found a mistake in my working, but like, okay. Wait, where is it? 23, okay. Bro, where is it? Okay, okay, I erased it, so it's chill, it's chill. Okay, I think we're finally moving on from Cauchy sequences. Okay, I don't know if you guys are happy or sad about that, but I'm kind of happy. Okay, finally, formal limit proofs. So, okay, well, this is still about kind of related to Cauchy sequences. So when you're doing formal limit proofs, it's basically all about inequalities. So some important inequalities to remember from calculus, like this one especially, absolute sine x less than equal to absolute x. Then the classic bounds on sine and cosine, you guys are used to that. Then this one about exponentials. So like e to the x is greater than equal to x, and also x plus 1 from Taylor's series. Similarly for log. So you should keep these in the back of your mind. And it's not always just going to be one term x. It could be some weird expression in there. But you can replace x with any expression that shows up in your proof. Then another thing is removing negative positive terms with an inequality. You might have seen me do it. It was when we had something like 1 on 2j minus 1 on 2k, and we wanted to bound this against epsilon. Well, it's two terms, but it would just be easier if we had one term. So this is just going to be less than 1 on 2j, because this term is going to be negative. So that's what I kind of mean by removing negative terms with an inequality. You just don't really need to care about them. And then sums to products. Well, you might have seen this in lectures, but like it's only when you have stuff like cosine something minus cosine something else in your proof. You might need to revise your sums to products identities, like cos A minus cos B equals whatever, because that helps you write it as an absolute value of a product. It's just way easier to deal with. Then here are some other tricks. Bounds involving k. For example, if you had something like 1 on k squared minus 1 on k, or plus 1 on k, and in your proof you want to bound this against epsilon, something you could do, just make it one term. So you can say k squared is greater than k eventually. So this is less than 1 on k plus 1 on k, less than 2 on k, and then now it's much easier to bound against epsilon. So that's what I mean by bounds involving k, or like n or whatever. Okay, here's another thing. Use the one norm instead of the two norm. So what do I mean by this? This is actually quite a useful inequality. The two norm of a vector is less than equal to the one norm. So the two norm, I'll just say for the two variable case, so root x squared plus y squared, that's the Euclidean norm, less than equal to the one norm, which is the absolute value of the sum of the absolute values of the components. Now, why is this true? Well, you can check this for yourself by squaring. Basically, this squared is, well, x squared plus y squared plus 2xy greater than equal to x squared plus y squared. Then you can take square roots. You can check this inequality for yourself, but it's useful because you don't have to deal with square roots anymore when you do this. You're trying to bound against epsilon. You can just write it in terms of this, and then you just have absolute values, no annoying square roots. So that's this inequality here. There's also the component norm inequality. I don't know if that's the actual name. I kind of just made it up, but like it makes sense. So given this, okay, basically the absolute value of a component of the vector is less than equal to the norm of the vector. So say the vector was like x1 up to xn, you can get this bound on the components of the vector. And you can check that for yourself, but it's basically just saying this. And if you square things, you can see it easier. Xi squared is obviously going to be less than equal to xi squared somewhere here, plus a bunch of other positive stuff. So why is this useful? Well, sometimes when you're doing the epsilon delta proofs, you might have this, but you just keep in mind that that also means you have the same bound for the components. So it's not just the bound on the whole vector, you also have the same bound on the components. So that's just a pretty useful trick. Okay, so we're finally done with this topic. Point set topology now. Okay, you guys know what this is. Actually, I shouldn't assume that. Okay, so a ball is basically the set of all x such that the distance between x and the center A is less than epsilon. So it's a ball with a center A and a radius epsilon, just like in R2, the classic is the unit ball. So it'd be, if this is 1, it's everything here. Because this is like the interior of a circle, basically. And a punctured ball is the same thing, it's just you don't include the center A. And it's written by this, with this notation, like, I think that's a O. So, but yeah, so it just means you don't include the center. That's why you have this here. This, it's not, notice it's not less than equal to, it's just less than. The distance from x to the center has to be positive, strictly. Okay, interior and boundary points. So an interior point is, so this is interior point of a set, basically. This is something you say in relation to a set. And it's just a point where there's a ball around it, fully contained in the set. So imagine I have the set is like this, interior of this. Take this point, for example. Is this interior? Well, yeah, because you can put a ball around it, and this ball is completely contained in the set. So, but if you have something like this, look at this point here. This is actually a boundary point, which we'll get into. Can you find a ball around this, which is fully contained in the set? Well, not really. You can try, but it's always going to have some point outside, right? So this would not be an interior point. And it's actually a boundary point here. A boundary point is a point where every ball around it contains a point in the set and a point outside of the set. So if you take any ball around this orange point here, okay, that's sad. If you take any ball around this point, you can try to imagine it. It's always going to have some point inside the set and some point outside the set. So it's a boundary point. Open and closed sets. So an open set is just a set which has every point interior. So all the points of it, for each point you can put a ball around it and it's completely contained in the set. And a set is closed if its complement is open. And there is another equivalent thing which we'll get into later. You can also say a set is closed if and only if it contains all of its boundary points. Okay, and then another thing is intersections and unions of open sets are open, and same for closed, but they have to be finite. There is something for infinite as well. I think infinite unions or arbitrary unions of open sets are open, and I'm pretty sure it's similar but for intersections for closed. There might be a question on this, like I think in some of the past papers they have like an example question where try to find a try to find basically an infinite intersection of open sets which is not open. So that would, you should probably look at that. Okay, so use the definition to show that this interval, this closed interval is, well, closed. So how do you do this? Well, the definition is complement is open. So if you want to show this is closed, we need to show its complement is open. I'll just draw it on the real line. This is the original set, and the complement would be something like this, right? Okay, cool. Now, how do you show this is open? Okay, so we need to show this guy's open. You just need to show every point is interior. So take an arbitrary point. For now, I'll just take an arbitrary point x on the left side. If it's on the right side, we can do the same logic, so I'll just do it for this side. How do we show this is interior? We need to show that there's a ball around it fully contained in the set. Now, what is a ball in R? Well, it's just an interval, like a finite open interval. So we need to find basically something like this. See, it contains, this is a ball around X, centered at X, and it's fully inside the set. But how do you write this with like a formal proof? Well, usually you just focus, I guess, on the distance between X and 4. You want to choose something smaller than that, right? So I'll just use absolute value for the distance. You can simplify it because you know X is less than 4, but it's fine. So this would be the distance. We'll choose a radius which is smaller. So a classic thing would just be to halve it. And you take the ball centered at X with this distance, then clearly this is going to be contained in the complement. And if you have it, if X is on the other side, you could do something similar, right? Ball at X, 6 minus X over 2. That would be half the distance, so it would be something like this. And then that proves basically that the set is open, because since X was arbitrary, we've proven every point is interior for this complement. And that just proves the complement is open, so that proves the original set is closed. Okay, I need to actually get a move on. Interior and boundary. Okay, so interior of a set is another set, and it's the set of all interior points. And boundary of a set is again another set. It's the set of all boundary points. It's denoted with this partial derivative symbol, even though it's not related to partial derivatives at all. I don't know why it's there, to be honest. Okay, so write a formal definition for a non-boundary point. Well, if you remember surely I have this. Okay, finally I actually have text on the slides. So a boundary point, this was the definition for all epsilon greater than 0. Basically, any ball centered at X will have a point in the set and a point outside the set. I think the intuitive definition is often easier to think about, because this epsilon delta definition doesn't help that much unless you understand it intuitively. So what would be the negation of this? Well, it would mean that instead of for every ball, it would be there exists a ball. And so this one is every ball has a point inside and outside. Negation would be there exists a ball where there's no points inside or there's no points outside. What that means is there exists a ball which is fully in the set or fully outside of the set. So basically it means a point is not a boundary point if and only if it's in the interior or it's in the exterior. Now, what is exterior? It's not really talked about that much in the course, but exterior of a set is the set of all points where there's a ball around it fully outside of the set. So something like all the way out here, you can find a ball which is fully outside of the set. So this would be like in the exterior. So if it's not a boundary point, it's either all the way out here or it's fully inside and it's an interior point. So if it's not boundary, it's interior or exterior. Okay, here are some important facts. You guys might have seen this, but if not, you can try proving them. The boundary is closed. This one's really useful. The boundary of a set is equal to the boundary of its complement. You can kind of imagine that it's, if you have something like this, the boundary of this would be like this guy here, the circle, and the complement would be the external thing here, and it would still have the same boundary, which is this orange circle. Then the interior is an open set, and the set is open if and only if it equals its interior. So you can have a go at proving these if you haven't before, but as like exercising the proofs regarding this topic. Okay, we'll actually do a proof together. So this is a really useful theorem. Elements of a set are interior or on the boundary. So how do we prove this? Firstly, we're going to take an arbitrary, okay, I think I actually have this. Okay, I'll go through it. So we'll take an arbitrary x in the set, and we need to prove it's interior or on the boundary. So, I mean, if it's interior already, then we're done, right? So we'll assume x is not interior. So I guess we can say x is not in the interior of the set. Now we just need to show it is a boundary point. So how do we do that? Well, if it's not interior, it means basically that there's every ball around it has a point outside of the set. So you can see that just from negating the definition of interior. But Basically, that means every ball contains a point outside of the set. Where when I say every ball, I mean every ball centered at X. So how do we show it's a boundary point? For boundary point, you need to show that every ball centered at it has a point inside and a point outside of the set. Well, we already got the outside part, right? And the inside part would, I guess, be X. This ball always contains X, right? And since X is in the set, what we've proven is that every ball centered at X has a point inside and a point outside. Therefore, it's a boundary point by the definition of boundary points. And yeah, so that proves that if it's not going to be an interior point, it has to be boundary, and that suffices basically. So this means elements of a set, like, they won't be in the exterior. So you can't be something like this where there's a ball around it which is completely outside of the set. Okay, limit points. So a limit point of a set is, first of all, it doesn't have to be in the set, but it's a point where there's a sequence of points in the set excluding X, which converges to X. So this caveat is pretty important. It's not saying there's a sequence of points in the set. It's saying there's a sequence of points in the set excluding X. That means your sequence can never actually equal the point X. But it does converge to X. There's an equivalent definition in terms of like topology, I guess. Now, what does this mean? It means every punctured ball around X contains a point in the set. So what does that mean? A punctured ball is a ball where you exclude the center. So this means every ball around X, excluding the center, would have a point in the set. So something like that. Now, it is useful to know both definitions. The first one is the actual definition and it comes up more often, but it could be useful to know this one for proofs. Okay, so here are some limit point theorems. I won't go through all of them because it'll take like a few years, but you can do it in your practice in your own time. So interior points are limit points, at least with respect to nice metrics. Limit points are interior or on the boundary. So, right, there's no way I'm zooming into this. Okay. So interior points are limit points are either interior or on the boundary. It can't be something like this point here, which is exterior, meaning there's a ball around it fully outside of the set. The limit point would have to be somewhere like here or here. And if X is a boundary point of the set, but it's not inside the set, then it is a limit point. This is also pretty important to note. Okay, closure. So the closure of a set is again another set, but it's the union of the set with its limit points. So you might not have seen this like notation. If the course uses this notation, they would define it in the exam. They'll say what it is. Omega prime is the set of all limit points of omega. So it's the set containing every limit point. And the closure is the union of omega with that. There's also an equivalent definition. The omega bar, or closure omega, is the union with its boundary points. That doesn't mean, by the way, that these two are equal, okay? It just means that unions are the same. So you can use either of them. I think this one's more useful in most circumstances. But yeah. Okay, now here's like a number one takeaway for closures. You really need to know this. Basically, X is in the closure if and only if there's a sequence in the set which converges to X. This is kind of similar to limit points, but not exactly because it's not omega set minus X. You're allowed to have any. It can just be an omega. So how do we prove this? Okay. So the first direction is pretty chill. So we'll assume X is in the closure. Then we just need to show there's a sequence in omega which converges to X. So obviously you just want to first of all expand this like with the definition, omega union omega prime, where this is the set of all limit points. So if X is in this, well, either it's in this one or it's in this one. If X is in omega, is there a sequence in omega which converges to X? Well, yeah, you can just basically take the constant sequence, the sequence where every point is X. Like, it's a bit trivial, but it does converge to X. And in the other case, if X is a limit point, well, by definition of a limit point, you already have a sequence in omega which converges to X. So that's basically the first direction proven. You can read this later on if you need to. Now the reverse implication would be if there is a sequence in omega converging to X, then it's in the closure. So we'll assume there is basically a sequence which converges to x, and now we need to show it's in the closure. So we need to show x is in omega union omega prime. That's meant to be an omega. Okay, so how do we do that? Well, if x is in omega, we're done, right? So we'll take the case where x is not in omega. Now we just need to show x is in omega prime. So x is a limit point. Okay, if x is not in the set, well, how do we show it's a limit point, right? We just need to show there's a sequence in omega set minus x, which converges to x. So we already have a sequence. We've assumed there's a sequence here. We just need to explain why it can never equal x, why all the points of the sequence are distinct from x. Well, if this sequence is in omega, I've just used the same set the whole time, but it's fine. So if x is in omega, x is not in omega, so it could be here if it's a boundary point, it could be outside. But this sequence is fully in omega. It can never equal x because x is not in omega. So this sequence is also a sequence in omega set minus x, and it converges to x. Okay, so that proves it. That proves x is a limit point. So x is in omega prime, and that means x is in one of them. So if x was in omega, we were done, and if x is not in omega, it has to be in omega prime, which is the set of all limit points. Therefore, it's in the closure. Okay, so just a brief summary. Closure is the union of the set with its limit points. It's also the union of the set with its boundary points, and this is a really important takeaway. X is in the closure if and only if there's a sequence which converges to x in the set. Now, with this discussion of limit points, you can define, or you can have all these characterizations of closed sets. So there's a lot of things which are equivalent. Obviously, closed is equivalent to the complement is open. That was by definition. Then there's also these two. So depending on the question, these can be easier, but only I guess if none of these are really working. So it also means that it contains all of its boundary points, which means if you have a boundary point of the set, then that has to actually be inside the set. So you can write it mathematically like this. Similarly for limit points. Okay, got some practice questions for you guys, and yeah, so you can look at these later when you're revising this. You can watch the live stream. And if you want the answer to question 4, like the solution, I'll just show it up here. This is the first part, and this is the second part. I won't go through it because it's meant to be a practice question, but you can check this out later on YouTube. Okay, this is a simpler example. Interiors and closures preserve subsets. So that means if you have a subset, A is a subset of B, then it means the interior of A is a subset of interior of B. And similarly for closure. So how do we prove that? Well, it's actually not too bad. For the first one, we'll assume X is in the interior of A. Now we need to prove it's in the interior of B. So what does interior mean? Well, it means there's a ball around X, so say radius epsilon, which is a subset of A, fully contained in A. Since A is a subset of B, you have this, so the ball is actually also fully contained in B. And that means that there's a ball around X, which is contained in B, so that means X is in the interior of B, and that proves the subset. So this first one is pretty chill. Second one's also not too bad, but I think it's easier if you use the sequence interpretation of closure. Remember what I said? X is in the closure if and only if there's a sequence in the set converging to X. So we'll suppose, I'm just going to write SPS for suppose. I'm not writing suppose every time. So suppose X is in the closure, then that means there's a sequence in A which converges to X. But the sequence is in A, right? So it's also in B because A is a subset of B by assumption. So that means there is a sequence in B which converges to X. So X is also in the closure of B. It's that simple. So yeah, using that sequence definition or interpretation of closure is pretty useful to use. Okay, now this one, I'll leave it as a practice question again. And yeah, I've said this like a few times. It's probably easier to use the sequence definition. So to do this, because this is to do with closure, right? This This basically says if you have a continuous function and apply it to a closure, it's a subset of the closure of the image. So you can do this one as at home, and this is the solution. You can check it out later. Okay, I think I'm on the last topic for my half. Actually, I'm not. Oh, wow, bro. Still have another one after this. Okay, so limits. So this is similar to sequence, but now you're taking limit of a vector valued function. So the output is a vector b, and you still have the similar epsilon delta definition. Now the limit is also unique, just keep that in mind. You have these nice theorems again. This first one is convergence of components. So it converges to b if and only if the components functions converge to b. So f of x is usually like f1 of x all the way up to say f n of x, where these things take in a vector and output a real number. And this last one here says the limit is b if and only if the limit as you approach a along any sequence is also b. So this is for any sequence xk which converges to a. It's more useful to use this when you're proving a limit doesn't exist, which we'll get to later. Okay, now the good old squeeze theorem, it also applies in like higher dimensions. So if you have, to have this inequality, we have it, the functions output real numbers, the real valued functions, just keep that in mind. So basically if you have this inequality for all x close enough to some limit point a, then also you have the limit of these equal, then f of x also squeezes to the same limit. This is just the squeeze theorem. We're going to be using this for a lot of proofs. So here are some nice tips and tricks to note. So first of all, if you want to prove a limit is 0, it can often be easier to prove the absolute value is 0. And that's actually equivalent. The limit as x goes to a of f of x equals 0 is equivalent, limit as x goes to a of f of x equals 0, is equivalent to, what just happened? Equivalent to saying the limit of the absolute value is 0. You can argue this by like the definition, you'll get some absolute value and you can prove this. Or you can even say like the absolute value is a continuous function. So you can use the continuous function limit theorem and say this is the same as the absolute value of the limit, which is absolute 0, which is 0. But yeah, anyway, this is pretty important when you're trying to prove a limit is 0. Secondly, just very basic inequalities from like positive or negative terms. We've kind of had a similar discussion on this trick before, but it's just very simple, like something like this. Just keep in mind you can, whenever you have a positive term, you can use it for an inequality like this. Then there's the AMGM. You might not have seen it in this form, but this is the superior form. X squared plus y squared greater than or equal to 2 absolute xy. And so this is useful when you want to bound x squared plus y squared. Now, if you expand this absolute value, you do get this, where you have xy in terms of x squared plus y squared. Sometimes it can be more useful to like think of it like this, but they are like equivalent. So yeah, we'll get an example where this is useful. Then there's the absolute value inequality. X is between its negative absolute value and its normal absolute value. You might think like, why am I mentioning this? But we will actually use this once. Triangle inequality. This is like the reverse triangle. This is the normal triangle inequality. Okay, now here's one of my favorites, the polar coordinate trick. Basically, you guys remember x equals r cos theta, y equals r sin theta. So since cos theta is less than or equal to 1, this is less than or equal to r. And similarly for this. Or you can just prove it directly from here. These two are going to be useful when you're doing squeeze theorem proofs, because especially when there's a lot of x squared plus y squared terms appearing, you can bound x and y against it and it just makes it easier. Cauchy-Schwarz inequality. So I think this came up in a lecture once. It's mainly going to be useful when you have an obvious sort of like sum product. So I think there was like xy plus yz plus xz, something like that. Just keep in mind that when you have something like that, you can bound it against this is like basically x1 dot xn, xn dotted with one end. You might have seen it like this, and then it's the norm squared of, it's the product of the norms basically. I'll just say y. Okay, and then here's a nice one. This is the bounding trick. I couldn't think of a more interesting name, but it's going to be this. Basically, if you have a function which goes to 0 and a bounded function, then the whole limit is 0. So sometimes this might be easier because there's an obvious function here which is going to go to 0, and you just need to prove the remaining part is bounded. Now this comes from the squeeze theorem basically, because if g is bounded and this goes to 0, you can easily prove with the squeeze theorem that the whole limit is 0. Okay, so we got an easy example here. Prove that this limit is 0. So usually we're going to try to use the squeeze theorem, and we're going to use the absolute value trick. So we're going to prove that the limit as x, where x is the vector x, goes to 0 of the absolute value is 0. I don't need to put absolute value on the denominator because it's always positive. So how do we prove this is 0 using the squeeze theorem? Well, clearly we have this. This is obviously greater than or equal to 0. The hard part is finding this bound. It's not actually that hard. So one way to get the less than equal to inequality is you do a greater than or equal to inequality on the denominator. Because that way when you take the reciprocal, it becomes a less than. So you can just bound this against something simple like x squared. And so when you do this, you get this bound. And if you simplify it, this is absolute x. And now 0 and absolute x both approach 0 as xy goes to 0, 0. Therefore, this thing here squeezes to 0. And since the limit of the absolute value is 0, the limit of the original function is also 0. So that's a pretty simple example. Right, I had another slide for this. Could have saved space. Okay, here are some practice questions to do. These all aren't too bad if you use the tricks explained in the slide. You can try doing them. It's pretty cool to try to use the polar coordinate trick. For example, for this one, you can basically show that this thing is bounded between like r to the 4 plus r to the 4, and this bottom thing is r squared, where r is square root x squared plus y squared, and you get this, and obviously this goes to 0. But you can check this out for yourself if you attempt these afterwards. Okay, now let's do a bit of a harder example. So we have something like this. How are we going to find this limit? Well, we could try to show it's equal to 0 using squeeze theorem. You can see that this guy here is going to go to 0 as xy goes to 0, 0. So maybe we can do something with the bounded trick. Maybe we can just show xy over x squared plus xy plus y squared is bounded. Because if that's the case, then from this trick here, the limit would be 0. Okay, so how would we prove this is bounded? Technically, okay, we can try to do the trick where you try to do an inequality on the denominator. So make this greater than or equal to something, and then we'll take the reciprocal and we'll get some less than equal to. So, I mean, we have x squared plus y squared. You might think of the AMGM inequality. X squared plus y squared greater than or equal to 2xy in absolute value. So you get this. Now what do we do? Well, there are a few things you could do. You could make this bound nicer by saying, first of all, xy is greater than or equal to minus absolute xy. Now, where does that come from? Well, there's the inequality absolute A is between absolute A and minus absolute A. So applying that here, you can say this is something like this. Now, if you didn't want to use that inequality, you could even just take cases for xy positive or negative, and you can get something similar. So basically we have, okay, now I can just look at this. So you get this here. Now if you take reciprocals on this part and this part, you get this absolute xy over this thing is less than or equal to 1. So that proves that this thing is going to be bounded. And when you multiply by x minus 1, x minus y in absolute value, you get this. And now both of these go to 0 as x and y approach 0. So the limit is 0 by the squeeze theorem. So yeah, that's just using the AMGM on the denominator. Here are some harder examples. You can try them later, but I won't go through them today. Okay, so proving a limit doesn't exist. Well, there was that theorem which states that limit exists if and only if it exists along any sequence. So to prove it doesn't exist, you usually find two sequences which approach the point, but it yields two different limits. So like it's a bit annoying to do it with sequences a lot of the time. First, you want to try to do it with a curve. So you might have seen so instead you can think of it as approaching along a curve in the xy plane, if it's say like a limit in R2, and then you can convert it to a sequence. We'll do some examples of that. So here are some possible example curves you might approach from. It doesn't have to be exactly like this. You might have y equals x, for example, y equals x squared, or it doesn't have to be y in terms of x, it could be x equals y squared, because this is still a curve in the R2 plane, as long as it's approaching, say, the right point. You will have some examples. But this thing is useful. This is like substituting a power function, so a curve which is like a power function, or just substituting along y equals 0 or x equals 0. And here's more of a niche trick which comes in useful in one of the examples we're going to go through. It's called the buffer trick. Actually, it's not called that. I made that up, but we'll call it that. So you approach the origin. Basically, you approach along the curve where you replace the denominator with a curve. So if you had something like, you approach along the danger zone where the denominator is 0, but you add a buffer term to it. It makes more sense with an example, so I won't go too deep into that yet. So determine if this limit exists. Now, one way to do it is approach along x equals 0. So we'll figure that out as a sequence later, but if that happens, then the function is 0 over 0 plus y equals 0. So when you're approaching along x equals 0, the limit's going to be 0. If you approach along y equals 0, however, then the function is this, right, which is 1. So the limit would be 1. Now you have two different curves you're approaching from, and they give two different limits. So the limit doesn't exist. If you want to write this formally with sequences, which I think probably you should do in the exam, the sequence is usually just something like 0, 1 on k. So this is like x, y equals this, and you take k to infinity. So then you'll get like limit as k goes to infinity of 0 over 0 plus 1 on k, which is 0. In the other case where y is 0, you can just say 1 on k is 0. And then you'll get 1 on k cubed on 1 on k cubed as k goes to infinity, and that equals 1. There's another way you could do it. That was the easiest way, but just to explain what this thing I mentioned before was, you could approach along y equals, say, x cubed or something. Why x cubed? Well, that just simplifies the denominator into one term. Like I'm matching the power here. If I approach along this curve, which definitely does approach the origin, then the denominator just becomes 2x cubed, which is a lot simpler to deal with. And you get half for the limit. If you approach along some other thing like y equals 2x cubed, for example, that's still approaching the origin, so it's a valid curve to approach from. You get x cubed over x cubed plus 2x cubed, which is basically 1 on 3, looks like. And that would have a limit of 1 on 3 as well. So that's kind of just showcasing this other, the power function path. Okay, so this one, funnily enough, this was in the last seminar, and we had like a really simple proof, but it turns out the proof was completely wrong, and this was actually quite a hard example. So we had to invent like a whole new trick to figure this one out. Okay, so we got the buffer trick today. Now, why am I using that? Well, first of all, like, you want to try simple stuff. Unfortunately, none of the simple stuff seems to really work here. Like, if you approach along y equals 0, you get 0. If you approach along x equals 0, you also get 0. If you approach along something like y equals like kx cubed, I won't use k, I'll use like m. Okay, I'll just say x cubed, for example. Then you get x cubed over 2x cubed, which is, x cubed on 2, right? That still would approach 0. So everything is literally giving you 0. You can test it for other stuff. We had to use the buffer trick. So basically I'm going to approach along something where I make the denominator equal to 0, but you can't exactly do that because then you can't really approach it like that if the denominator is always 0. So you add like a buffer term. Instead of approaching along y equals minus x cubed, which would screw up the denominator, you add like a buffer term like f of x. We'll figure out what this is. Now, since everything is like power functions here, maybe we can make maybe we can make our buffer term like x to the something, x to the n, for example, and we'll figure out what that n is. Then if you approach along this curve, as x goes to 0, 0, clearly this would approach 0, as long as n is, I guess, positive, right? So that is a valid way to approach this point. If you wanted to write it in terms of sequences, it would be like k and then, 1 on k and minus 1 on k cubed plus 1 on k to the n. Notice that here y is still equal to minus x cubed plus xn because x is 1 on k. But yeah, so what happens if you do this trick? Will it actually help? Well, if you sub that in, you get x cubed minus x cubed plus x to the n over x cubed, y plus x cubed becomes now x to the n. When you simplify this, you get, I think this. Now as x goes to 0, what happens? Well, this guy just disappears. And we want to choose n so that this will not give us a limit of 0, because all the other stuff we've tried gives us a limit of 0. If we want to prove it doesn't exist, we need another number, so the limit would not exist in that case. If we take n equals 6, for example, then this is just x to the 0, right? It's going to be minus 1. And so this is a case where, so if we actually approach along minus x cubed plus x to the 6, you'll see that the limit is minus 1 and not 0. Now, so this buffer trick is a bit niche, but I guess nothing else really worked here. Well, this was the easiest path we could come up with. Okay, some other cooked examples. You guys can try this later on. So I won't go through all of them. This is more like for practice. Okay, continuity. So continuity is similar to this. It basically means the limit as you approach the point is the value of the function at the point. So you need the function to actually be defined there. It needs to have a limit exist there, and it needs to equal the value of the function at the point. So it's similar to a limit definition. And this is what it would be like for two variables. And you say a function is continuous on a domain if it's continuous at every point in the domain. So this limit holds for every point in the domain. Now, we'll leave this as an exercise. I've said that too many times, but this is from like final back in the day, 2018. It's not really too bad. You just need to prove that it's not continuous there, which means you need to prove the limit is not equal to the value of the function at the point. So you just need to prove the limit is not 1, and so it's kind of doing something similar to what we've been doing. You're considering approaching the origin from different curves and trying to get a different limit to prove it doesn't exist. Okay, somehow I have to get through this. We're definitely going over time, so I'm sorry about that. So properties of continuous functions. So first of all, there's a lot of focus on preimages in this topic. A preimage of a set, this S here would be something in the codomain. So if this is the domain and this is the codomain, the preimage is everything which maps into that set. So if this is a set S, then the preimage is F inverse S. Everything, this is the set of all X which will map into the set S based on the function. So this is important. X is in the preimage. So by the way, the preimage itself is going to be in the domain, but this thing is in the codomain. So X is in the preimage if and only if f of x is in S. Okay, so here's the main two theorems about continuous functions and preimages. If f is from, say, omega to Rn, and omega is open, this is really important, the domain has to be an open set. Then f is continuous if and only if the preimage of an open set is open. So if U is open in R, okay, I'll guess Rn. I guess this would be Rn to Rm in this case. Sorry. I guess a subset of Rn. So if you have U, which is open in the codomain, then the preimage is open in the domain. So this is equivalent to saying continuity. You have something similar for closed sets, but important caveat, it needs to be defined on the full space. The original one, you had the domain can be just in any open set in the Rn, I guess. Here it has to be defined on the full space, and the preimage of a closed set would be closed. Then this is more like used for proofs of this, but you can prove this as an exercise, trust. Okay, preimage. So here are some nice identities for preimages. This one came up in like I think one of the tutorials, like you needed to use this. Preimage of a complement is the complement of the preimage. Then also preimages work really nicely with intersections and unions. You can just expand it out like this. And they also preserve subsets. Note by the way that you can't really compose preimages like this and expect to get back the original thing. It doesn't work like an inverse function really. So just keep that in mind. Because A is a set, by the way. Okay, so using this, we basically have more options now to show a set is open. You don't have to do it by definition every time. You can show it is by definition as well, or you can show the complement is closed. This one you might not have seen that much. A set is open if and only if its complement is closed. And the other one is using that preimage thing. So you just need to write the set as like the preimage of an open set. Because the preimage of an open set would be open if you have F as continuous. And if you want to show a set is not open, you can show the negation of any of these. Similarly, for showing a set is closed, contains all its limit points, boundary points, or you can say its complement is open, or you can use this preimage thing. Like sometimes you're not always going to use this one. Just keep in mind there's lots of ways to prove a set is closed. Okay, so here's an example. So you have this, we want to show this is open. What is this really? Well, it's all of R2 excluding this, which is actually like the graph of f of x. So it's all of R2 excluding a graph, and we want to prove it's open. Now one way to do this is show its complement is closed. So we'll prove that the graph is a closed set. And how would we prove it's a closed set? Well, there's also many ways to do that. We're going to use the limit point definition, and the reason is because continuous functions work nicely with limits. You can use limit theorems with that, and that will make things easier. So, okay, do I leave this as an exercise again? Okay, maybe I'll do it. So we'll show that this contains all of its limit points. So how do we show that basically? Well, we just need to say let x, y be a limit point of the set. I'm going to say this set is G. We just need to say now, we just need to prove this is inside G. That would be proving that any arbitrary limit point is in the set. So if it's a limit point, there's a sequence, I'll say like bold xk, which converges to xy, and this sequence is in G, excluding x. That's what it means for a limit point. Now, by convergence of components, you have xk approaches x, yk approaches y. Now, because xk is in the set G, what does that mean? Well, it means it's like a valid point of this graph. So it means it satisfies this relationship between the components. F of xk is going to be equal to yk, because we assumed xk is in G. So this here actually means that f of xk approaches y, because yk is f of xk. Now, because f is continuous, and if you remember, when you apply a continuous function to a limit, it just works the same. So this means f of xk also approaches f of x, where this is a different sequence. So now you have f of xk approaching two things, but the limits are unique, so it actually means y equals f of x. So what does that prove? That proves xy is a point in G, right? Because if y equals f of x, then xy is in G. So that proves that any limit point is inside the set. So that proves that G is closed, so the complement is open. Okay, now using preimages and stuff, you can get these two really nice results. Basically, if you have this less than equal to inequality, and these are all continuous functions defined on the full space, this actually is a closed set. So you have something similar for open. If it's a strict inequality, this would be an open set, and it has to be defined on an open set. Now, I'll just prove one of them. So the trick is you bring everything to one side. So this set is the set of all x such that g of x minus f of x is greater than or equal to 0. One way you could write this is it's in 0 infinity, right? So this is actually like a pre-image of a function. Like if you define h of x equals g of x minus f of x, then the pre-image h of this guy is the set of all inputs such that h of x is in this. So it's the set of all x such that h of x is in this. Now isn't that exactly what we have here? Now, since g and f are both continuous, h is also continuous. So this thing is the pre-image of a continuous function of 0 infinity. Now 0 infinity is a closed set on the real line. So 0, it's a closed set. So pre-image of closed set is going to be closed because this is continuous. So this proves that this guy is closed. You can do something similar to prove this thing is closed. And now for this set here, this is now going to be the intersection of both of those sets. So it's going to be the intersection of this thing with, say, oh, I realized I shouldn't have used h of x for that thing. H of x is something different. Let's just call it phi as usual. Where phi is g of x minus f of x. Yeah, so this is just the intersection of the set of all x such that f of x is less than or equal to g of x, and this one. And the intersection of two closed sets is closed, so therefore that's closed. You can do something similar for the open ones. Bro, I had the proof here the whole time. Okay. Compact sets. So a set is compact means it's closed and bounded. You already know closed set. A bounded set means you can put a ball around the set and it fully contains it. So it just means that everything satisfies the distance, or the distance of x from 0 is less than or equal to some specific n. And this is an important theorem. Continuous functions preserve compactness. So if you have a continuous function and you have a domain which is compact, or it can be a subset of the domain, then when you apply the f to it, it's also compact. Then there's path-connected sets. We had an assignment on this, so like, surely you guys know this, but might have forgotten some features. So path-connected, a set is path-connected if and only if for any 2 points you can find a continuous function that connects them, basically. And so it would be something like this, where phi of 0 is the first point and phi of 1 is the second point. Continuous functions also preserve path connectedness. So there's a lot of theorems here about continuous functions. If k is path connected, f of k is also path connected. Then there's another one where the union of two path connected sets is also path connected, only if you have this condition. They can't be disjoint sets. So like if I had two disjoint sets, obviously the union is not path connected because there's no way you can get from this point to that point without leaving the set, right? You need to have a actual non-disjoint, like it needs to be a non-empty intersection. They have to intersect somewhere. And then you can say the union is path connected. Okay, so for time constraints, I'm just going to use theorems to like one-shot this one. But you guys can also try to do this using like from definition. So first of all, we'll sketch this set. It's basically like the unit disk, right? But with some other condition. X squared plus y squared less than or equal to 1, something like this. But we need xy greater than or equal to 0, so that means they have the same sign. So I guess it's like the first quadrant and also the third quadrant. Something like this. And you do include the origin and endpoints. Now, is this path connected? Well, intuitively, it's like obviously path connected at least in each individual part. And if you have 2 points in something like this, then I guess you can join in something like this to prove it's path connected as well. I'll leave it as an exercise to prove directly this one, but you can also argue this with theorems. If you take for granted that a disk is path connected, so x squared plus y squared less than equal to 1 is path connected, then these two are both subsets of it. So they're both path connected. Subsets of a path connected set are also going to be path connected. And then you have a union, you have a union of two path connected sets, which are, and they do intersect, right? Because they intersect at the origin. So you have a union of two path connected sets, and they do intersect somewhere, so the union is also path connected. That's basically what this is here. But if you wanted to prove directly that it's path connected, you would basically take 2 points, x and y, arbitrary points, and probably the easiest way to join them is by drawing a line from x to the origin, and then drawing a line from the origin to y. So you can have a go at that to prove it's path connected. You might need to write out the full path with all the parameterization and stuff. Okay, so if you want to show a set is not path connected, here are some tips and tricks. You might have used this in the assignment. Basically, suppose by contradiction there is a path connecting 2 points, but you choose the points cleverly. So you choose points where it's obvious there's not going to be any path. You just need to prove it. So you suppose by contradiction, and then because you have a continuous path, you can use things like that path is continuous on the closed interval 0, 1. And you can use stuff like intermediate value theorem on the components or the path itself to show that somewhere in between the endpoints, it leaves the set. So, like if you had something, I think there was an example about, okay, so say you had some curve like this. I guess this is just like the tan function. But say the set is like all of this. This won't be path connected because you have an asymptote here. If I had, say, a point here and a point here, there's no way you can join them up without leaving the set because of this asymptote. So you can try to use something like intermediate value theorem to show that it will equal, if you have a curve between them which is continuous, it will actually enter this point on the x-axis. Okay, so I think one last example and I'm done. So this is a bit of a difficult one. Let K be the closed unit ball in R2. So that's just, okay, I've drawn this a few times, but it's just something like this. And it's the closed unit ball, so it's including the outer circle as well. And let F be continuous, it takes in any point in this unit ball and outputs a real number. Now, explain why it's a closed finite interval in R. Okay, so you have a continuous function. The good idea here would be to use all the theorems you know about it. You know continuous functions preserve path connectedness and also compactness. Path connectedness and compactness. So maybe we can try to use that because this ball is clearly compact, it's closed, it's also bounded, and it is path connected as well. So f of k should be closed and bounded, and it's also path connected. So keep in mind, f of k is on the real line. It's a set in the real line. So the only closed and bounded sets in the real line, the only path connected sets in R are actually intervals. So you know f of k is some sort of interval. It could be a finite interval, infinite interval. But the thing is, we have this extra condition, it's closed and bounded. So it has to be, because it's bounded, it has to be finite, can't go off to infinity, and because it's closed, it has to be something like this. And I'll call these A and B for the next part. So this proves it's a closed finite interval in R. Okay, this next part is actually like way harder. Deduce that F cannot be injective. Okay, so injective means one-to-one. So we'll try to do something like contradiction. Suppose it's not injective. Okay, so now what? Well, if you're trying to do a proof by contradiction, you need to figure out, maybe it's useful to think where would you get the contradiction from. You could try to contradict some of the assumptions you have, like F continuous, for example. Maybe we can try to contradict that. But one thing I want to stress is like, always try to use the powerful theorems that we've learned in the course, because doing everything from definition sometimes is just way harder, and theorems can just like one-shot a lot of things. So what are the theorems we know about continuous functions? they preserve like path connectedness, for example. So how would we use that to get a contradiction? Maybe we can show that it doesn't preserve path connectedness. Maybe we can find some set which is, let's say S is path connected. I'm just going to use PC. And we have f of S is not path connected. Because wouldn't that mean f is not continuous? Because you have a path connected set, but f of S is not path connected. That would contradict this. So instead of contradicting continuity directly, we'll try to do it via this approach. Okay? So first of all, we're a bit lucky here because f of S is in R, so it's a lot easier to deal with. You want a set in R which is not path connected. But keep in mind it's technically going to be in f of k, which is the image, and the range is basically like a closed interval, right? So f of S would be some not path connected set we're trying to find in here. Now, what's the simplest example of a non-path connected subset of this? Maybe it could be something like this, where I literally just removed an interior point C, for example, because this wouldn't be path connected because there's no way to get from like here to here. Or you could even do disjoint sets. Could do something like this and then this. This would not be path connected, but we'll do the first example. The goal is to basically, we need to remove a point from AB. Now, can we get a set, because f is injective by our assumption, wait, I'm a bit special, okay. I meant to say it's actually is injective by contradiction. Suppose it's injective. So, if it's injective, that means when you're mapping from the ball to AB, it means basically everything in AB is achieved once. You can't have it be achieved multiple times. And that's basically what one-to-one means. So if we're going to remove some point C from the AB, let's say it has to be in the interior, because if we remove the point A, this would also be a valid subset, but this is still path connected. So technically need to remove an interior point. So you can say A plus B on 2 if you want, but we're just going to say choose some C in AB. Now, because we're assuming this is injective, C is only achieved once. There's exactly one x in the unit ball, closed unit ball, such that f of x equals C. There can't be multiple, otherwise it won't be injective. We're assuming it's injective by contradiction. So now we're going to consider, we want a path connected set in the unit ball, right? But we're going to remove, we want f of S for whatever path connected set we're using. We want f of S to be not path connected. We want it to actually be like something like this, union CB, where you remove C. Well, we can just think about removing the point X. Imagine this is X, whole unit ball, but you exclude one point. Now, is that path connected? Well, yeah, it is actually still path connected, because you can always just avoid that point, basically. I think for the purpose of this question, you don't need to prove rigorously why this is path connected. Just say like, it is path connected. So this is still path connected, but when you apply F to it, you get this, which is not path connected. So that's a contradiction, and therefore that contradicts F being continuous by that theorem. So it can't be injective. So yeah, this is a cooked question, but I guess like the lesson is contradiction is really useful sometimes, and try to use the powerful theorems you've learned in the course, because it can simplify things a lot. Okay, so we have the BWT here. Okay, this is mainly used to prove BWT. It probably won't be that important for the exam. But it basically states that every sequence has a subsequence which is like monotonic, so like non-increasing, non-decreasing, increasing, decreasing, etc. But this is the main theorem to know, BWT. A set is compact if and only if every sequence in the set has a convergent subsequence whose limit lies in K, lies in omega. So basically any sequence xk, so K is from 1 to infinity, has a subsequence xkj, that just means you take some points of the sequence and get a new subsequence in order. And the limit, this is convergent and its limits is some x which is in the set. So yeah, okay, I think you guys want another exercise, don't you? So let's do this as an exercise. I'm leaving it as an exercise, I'm not going to do it. So this is just use the BWT to prove that f is compact and continuous and f of k is compact. So this is proving basically the compactness theorem, like continuous function preserves compactness. It's from the supplementary exam. I don't even know how we got that, but okay. Like maybe someone did it and got this question. Okay, I think this is it for me. I might have gone like a lot over time, so my bad. But yeah. Okay, now we're moving on to Lit.
Hey guys, I'm Yui and I'm going to be going through the second half. So, first things this. Starting off with differentiability, we have our partial derivative. So, when we have a partial derivative, for example, f with respect to x, what this means is that we are treating our x as our variable and our y as our constant, right? And just like with one variable, we can also write this in terms of first principles. So in terms of fx, we can write our x plus h here. And similarly, for our partial derivative with respect to y, we are treating our y as the variable and our x as the constant. Except for our first principles, we are doing y plus h instead of x plus h. And now moving on to our chain rule. So we suppose that f is a differentiable function of two variables x and y, and that x and y are differentiable functions of two variables s and t. So we can express a function, capital F of st, as this here, right? Now we can do our chain rule and perform it using df ds. So when you first look at this, it doesn't look very intuitive, but what this derivative is essentially saying is that you're applying this derivative to f in both the x and y direction, right? So for example, for the first component, you have df dx, which means that you're applying the derivative in the x direction, and because your x is in terms of s and t, you have to chain rule it with the dx on ds. And the same applies for our second component. You're applying the derivative to f in the y direction, and because y is in terms of s and t, you want to chain rule it. So that's where the dy on ds comes from. And similarly, for your partial derivative for df on dt, it's the same exact logic, so I'm not going to go through that. Okay, so starting off with our first question. We are given that f of s of phi of st is equal to 0, and that this holds for all st, right? Now, assuming that our partial derivative with respect to y is not equal to 0, we want to prove that this is true. Okay, so when you first look at this, it doesn't look very straightforward, but the trick here is to just apply your partial derivative with respect to s to this line here. So I'm just going to move down a little bit so you can see what you're trying to prove. You have that your df on ds is just equal to fx plus fy phi of x is equal to 0. So I just applied df on ds to the line here, right? And now, from here on, you can also apply df ds again. So if you apply df ds of this line here, so you have your fx plus fy phi. Oh, sorry, this should be s, not x. Let me just fix that. So phi s is equal to here. You get that this is equal to fxx plus fxy phi of s. And because now your second component is basically just a product. You can use product rule, right? So from here on, you can write this as fyx plus fyy phi s. And because you diff the first one, you leave the second one the same, so that would just be phi s. And then you want to leave the first the same and diff the second one, so you have plus fy phi ss, right? And of course, this whole thing here is equal to 0. If you simplify the left-hand side, you get that fxx plus 2fxy plus fyy bracket phi s all squared plus fy phi ss is equal to 0. And from here on, you can kind of just rearrange it, and you should be able to get the solution. So I'm just going to draw an arrow, and you can rearrange that yourself. Okay, and now moving on to a harder version of the chain rule. Consider some region omega, which is a subset of Rn, and omega prime, which is a subset of Rm. And we let x naught to be some interior point inside our omega, right? Now we suppose that f, which is a function, maps from omega all the way to Rm, and that g also maps from omega prime to Rk, with f of omega as a subset of omega prime. So what we can say from this is that if f is differentiable at x naught and g is differentiable at f of x naught, then the composition g of f at x naught, then g of f is differentiable at x naught, and this expression here is true, right? And for those who don't know what the D here represents, it basically just represents the Jacobian matrix. And for those who forgot what that is, it's this matrix here. So yeah, that's our Jacobian matrix, which is also our D in this case. Okay, so moving on to our next chain rule question. Let's consider some function f of r theta, which is in terms of r cos theta, r sin theta, right? This is basically just, you'd recognize the polar coordinate map. And let us also consider some other function. Say g of xy is equal to x squared y plus y cubed, right? Now we will define our function h to be a composition of these two functions. So let's call it g of f. So using chain rule, we want to find the derivative of h of r theta. Okay, so from here we kind of just use what we saw from before, our chain rule. So we have that d of f of r theta is just equal to cos theta sin theta minus r sin theta r cos theta, right? And this is basically just you diff the function with respect to r in the first column and with respect to theta in the second column, right? And now you also do the same for the function g. So dg of xy is just equal to 2xy because you diff the component with respect to x, and then you have x squared plus 3y squared in the second component because you differ with respect to y. And now from here, you kind of just apply the chain rule. So you have that dh of r theta is just equal to 2r squared cos theta sin theta r squared cos squared theta plus 3r squared sin squared theta, right? And now you kind of just want to attach this at the end. So you multiply this entire thing by cos theta sin theta minus r sin theta r cos theta, right? And I trust that you guys can do the multiplication yourself. If you simplify this whole thing, you get that this is equal to 3r squared sin theta, and our second component is r cubed cos theta. So that would show Okay, yeah, there we go. Yeah, so that's our answer right there. And now moving on to our affine maps. Yeah. So we have our two definitions. So our first definition is we consider some function t that maps from Rn all the way to Rm. We say that this is called affine if there exists some y0, which is an element of Rm, and a linear map L, which maps from Rn to Rm, such that this thing here is true, right? And then from this, it kind of follows that f is said to have an affine approximation at point A is an element of omega if there is a matrix A and a vector B such that this expression here is true. And if this expression is true, we say that the affine approximation is given by g of x is equal to ax plus b. Okay, and now moving on to differentiability. So this is kind of just an extension of the stuff from above, except now we know what an affine map is, so we can kind of define it in a better way. So we say that a function f is said to be differentiable at a if f has an affine approximation at a, right? And we say that a function f is differentiable if and only if there's an affine map D such that this thing here is true. So you can see that differentiability is very highly correlated to the above, right? And from here, you have a very nice theorem that says that if you have some region omega, and that A is in this region omega, which is an interior point, and f is a function, then we can say that if f is differentiable at A, and all partial derivatives exist, and this thing here is true. And you will recognize this as what we did from before, which is just the derivative is just equal to the Jacobian, right? And now we have more theorems. So these theorems just connect differentiability with continuity. Okay, so we can suppose that omega is open, if that would move. Okay, there we go. Sorry about that. So for our first theorem, we suppose that we have this region omega, which is just some open region, and now we have some function f, which maps from omega all the way to Rm, right? If these partial derivatives exist and are continuous on omega, then what we can say is that f is also differentiable on omega. And it's also very obvious from here that if our function f is differentiable on omega, then f has to be continuous on omega, right? So that's very intuitive. And an important note you want to remember is that a function can have partial derivatives, be continuous, but still not be differentiable. Okay, so now we will move on to our question. If that would load properly. Yeah, okay. So suppose we have some function f x y and we define it like a piecewise function. So we have this expression when x y is not equal to 0, 0 and 0 otherwise. And we want to determine all variables of alpha k m, which is an element of natural number where all partial derivatives exist for the first part, or f is differentiable for the second part, right? So I've kind of just typed that up. First, you want to realize that we require k plus m to be greater than 0, right? Because if we look above here, if we're solving the point 0, 0, you know that 0 to the power of 0 doesn't exist. So that is why k plus m has to be greater than 0. Then we simply just use the definition. So fx 0, 0, you kind of just use the limit definition we saw from before and sub everything in. And you also obtain the same for Fy of 0, 0. Okay, and then it follows that you can kind of just use your squeeze theorem on this expression here, right? And because you know that your sine of 1 on h squared is always bounded between minus 1 and 1, you can kind of squeeze it between these two functions here, right? And then we know that h to the 2 alpha minus 1, the absolute value of this approaches 0 when alpha is greater than half. So basically what we can say is that it follows by the squeeze theorem that this limit is equal to 0 when alpha is greater than half and k plus m is greater than 0. Okay, and now for part 2. So basically here we also just kind of apply our theorem from before. We say that f is differentiable when this expression is equal to 0. And it follows from the previous part that fx of 0, 0 is equal to fy of 0, 0, which is equal to 0. So therefore we can conclude that Jacobian 0, 0 is just 0, 0, right? So therefore a condition here just reduces to this here. And then from here you kind of just use your triangle inequality. So you can kind of split these two up and write the sum as two separate sums instead. And since you know that is true, you can just divide the left hand side and the right hand side by the square root of x squared plus y squared. Okay, and now a trick you can do is to just let r to be equal to the square root of x squared plus y squared. And note here that our absolute value of x is always less or equal to r, and our absolute value of y is always less or equal to r. So you can express this expression to be less or equal to k plus m minus 1. So then from this, we can express the previous expression as this here. So you can say that when this expression approaches 0, right, this only occurs when alpha is greater than half and k plus m is greater than 1. So therefore, these conditions ensure that f is differentiable. Okay, and now moving on to our affine approximation. So we want to find the best affine approximation to the function f, which maps from r to the r2 of this thing here at the point 1, 1. So once again, you kind of just use the formula. A lot of this is just a lot of computational stuff. So the best affine approximation at, let's say, core A11 is given by this expression here, as you've seen from before. And the sign here is just the Jacobian, right? So the first column, you just differentiate with respect to x, and the second column, you just differentiate with respect to y. And from here on, you can just kind of put everything together by subbing in the point 1, 1. And that's kind of just what you get at the end. Okay. Yeah, sorry about that, guys. It's like really laggy. Okay, so moving on to differentiation along curves. It's fine. So for a path C, if it's differentiable at t, then its Jacobian is the element-wise derivative of its component. So that means when you do c dash of t, you differentiate each component-wise. So you have your c1 dash of t all the way to cn dash of t. And for our definition, let's consider C that maps from I all the way to Rm be a path, and let T naught be an element of this path, right? And we say that the derivative of C dash of T naught exists and is non-zero, then C dash of T naught is called the tangent vector, or essentially the velocity of C at T naught. And this is denoted by our V of T naught. And from here, you can kind of, I guess, elaborate on this and say that the absolute value of V of T naught is equal to the square root of the dot product of V of T naught dot V of T naught, right? And you can also elaborate more on this and say that your acceleration is just equal to your velocity derivative with respect to T. Okay, and now moving on to another question. So we are given R that maps from R to R2, and we're defining it as this, right? When you first look at this, you probably think, oh, it looks really messy, but what you can recognize from this is that it's basically just cosh on the top and shine squared at the bottom, right? And the way I got that is, for the first component, I divided the top and bottom by e to the t, and then for the second component, I divided the top and the bottom by e to the 2t, right? And from here, because we know that cosh squared minus shine squared is just equal to 1, you have that x is equal to cosh t, y is equal to shine squared of t, so therefore y is equal to x squared minus 1. Okay, and now for our next question, we want to find the speed and acceleration at 1, 0, and we also want to determine whether a tangent exists at this point, right? So one way to go about this is just differ 2 times. So you have that at 0.10, we can kind of just sum everything in and deduce that t is equal to 0, right? And from here we have that r dash of t is equal to cosh t to shine t cosh t, right? And this is basically just using the fact that r of t is cosh t shine squared t. Okay, and what you do now is you just sub in the point t is equal to 0, right? So you have that r dash of 0 is, let me make that a bit neater, is equal to 0, 0. So what you can say for this is that, therefore, speed is given by the absolute value of r dash of 0, which is equal to 0, and note here that the tangent doesn't exist at r dash of 0 has no direction. Okay, so there's that. But then we still have to find the acceleration of this as well. Yep. Oh wait, sorry, this should be shine t. Because you diff the cosh, so it should be shine. But yeah, you just sub everything in and you should just get that. Okay, and now we want to find the acceleration. So we have that r double dash of t is equal to cosh t to cosh squared t plus 2 shine squared t, right? And from here, you can't just sub in t is equal to 0 again. So you have that a is equal to r double dash of 0, which is equal to half. So that is your acceleration. Okay, and now moving on to the gradient. Let's consider some region omega and some function which maps from omega to r. So basically we say that the Jacobian is referred to as the gradient of f, and we denote this by the upside down triangle nabla of f. And for here you can just write it as like partial derivatives and put it into a vector, right? So first component you diff with respect to x1, second x2, and all the way. The last one you diff with respect to xn. Okay, and now we suppose that f is a function of 2 variables, and that fx, xy are continuous r, a, b. Then what we can say is that the gradient of f, so nabla of f, is basically just fx of ab as the first component and fy of ab as the second component. Okay, so that's that section done. Now we're gonna move on to directional derivative. Okay, so this is just very similar to our definition from before, except now it's with respect to directional derivatives, right? So let's consider A to be an interior point of omega and let U to be a unit vector in Rn. So we say that the directional derivative of f in the direction U at A is defined by this here. So this is just basically our first principles definition. And this only occurs if the limit exists, right? And then it follows that if f has partial derivatives continuous, then the directional derivative of f in the direction u at A is given by this expression here. Okay, so for the next one, it's basically just the same thing as before, except now we are saying that f, well, let f be differentiable at x naught, which is an interior of omega. If we say that phi is an element of Rn excluding 0, then the directional derivative dv f of x naught exists, and that this thing here is true. So note here that it doesn't look very useful, but that the contrapositive is useful for proving that f is not differentiable at x naught. And you will see later how this is used. Okay, so this is another question. So we're defining f of xy, again, as a piecewise function. So when xy is not equal to 0, 0, we have that this is true. And when it is equal to 0, 0, you have that f of xy is equal to 0, right? Okay, so what this question wants us to do is to first consider phi, a vector, 1, 1, and show that f is not differentiable at 0, 0, right? So what we can do here is just kind of a bunch of tedious algebra. So we have that fx of 0, 0 is equal to the limit of as h approaches 0 of f of h0 minus f of 0, 0 over h, which is equal to 1. And we also have that fy of 0, 0 is equal to limit of as h approaches 0 of f of 0 h minus f of 0, 0 over h is equal to 0. So then it follows that nabla f of 0, 0 is just equal to 1, 0, right? Okay, so that's that done. Now we want to normalize our vector 1, 1. So we are given that, let's go move down, phi is equal to 1, 1. So therefore, our normalized vector is just 1 over square root of 2, 1, 1, right? And it follows from the previous definition that directional derivative at 0, 0 is just equal to nabla f of 0, 0 dot product normalized vector. And this becomes 1 on square root of 2. Okay, so that's kind of like the first part done. Now we want to confirm using the first principle definitions to see whether that's true, right? So we have that by computing it directly, we have that dv f of 0, 0 is equal to limit of as h approaches 0 of f of h on square root of 2, h on square root of 2 minus f 0, 0 all over h. And this is just a bunch of tedious algebra. You notice that f of h on square root of 2, h on square root of 2 is just equal to h squared on 2, h on square root of 2 over h squared. And if we simplify that, that becomes h on 2 root 2. So therefore, you can say that dv f 0, 0 is equal to the limit of as h approaches 0 of h on 2 square root of 2 all over h. And if we simplify that, that becomes 1 on 2 square root of 2. And that is not equal to 1 on square root of 2. So therefore, we have proven that the two values are not equal. And from the previous theorem, it holds that f is not differentiable at 0, 0. so moving on to the gradient. We say that for a function of two variables with nabla f of x naught is not equal to 0, then the maximum and minimum values of du f of x naught are plus minus the magnitude of nabla f of x naught. And they occur in the directions given by plus minus nabla f of x naught, right? And we also say that this here is normal to the level function passing through x naught, provided that f has all partial derivatives continuous at x naught. Okay, and now this is another question. So we are given that f of xy is xyz is equal to x squared plus y squared plus z squared. So at the point 1, 1, 2, we want to find the directional derivative in the direction normal to a sphere, x squared plus y squared plus z squared is equal to 9, and pointing towards increasing x. So for this question, you kind of just compute the nabla f. So you have nabla f is equal to 2x, 2y, 2z, right? And from here, you can't just sub in the points. So nabla f of 1, 1, 2 is equal to 2, 2, 4. And here, you kind of just want to normalize it. So that is just equal to 2 on the square root of 24, 2 on the square root of 24, 4 on the square root of 24, right? And using that, you can just compute the partial derivative, sorry, not partial derivative, the directional derivative using the formula from before. So you have that dv f is equal to 1, 1, 2, dot product 2 on the square root of 24, 2 on the square root of 24, 4 on the square root of 24, which is equal to 2 root 6. And note here that if the question asks for it in the direction tangent to a sphere, then our directional derivative would just be 0 because it will be orthogonal. Okay, and now moving on to tangents and normals. So for our tangents, we say that for a surface S defined by phi is some constant, the tangent plane at P, which is an element of S, is the plane through P with normal nabla phi of P. So from this definition, we can kind of write it as this form here. And you can also kind of just draw this out to show that it's true. And note here that x just kind of represents x, y, z. And our P represents P1, P2, P3, which is just an element of our three-dimensional space. And for normal, it's kind of the same thing. So for surfaces in R3, the normal line at P is the line normal to the tangent plane at P. Okay, and now for another question. So we want to find the tangent plane and normal line to the surface defined by this here at the point 2, 0, square root of 2, right? So I guess the first thing you can do is to define phi to map from R3 all the way to R by phi of x, y, z is equal to x squared plus y squared minus z squared. Then we have that phi inverse of 2, which is the level set where phi is equal to 2 defines the surface, right? And from here, kind of like the same concepts as before, you can just kind of find nabla phi of x, y, z. So you have that nabla of phi x, y, z is equal to 2x, 2y minus 2z. And we can say that this is normal to the surface. Okay, so now you have that, you can't just sub in the points. So nabla phi of 2, 0 square root of 2 is just equal to 4, 0 minus 2 square root of 2, which is, if you factorize the scalar of 2 out, becomes 2 of 2, 0 minus square root of 2, right? And from here, you can kind of create your line, your normal line to the surface. So you know that the line passes through the point 2, 0, 0, 2, right? So you can say that the normal line can be given by 2, 0, square root of 2 plus lambda 2, 0 minus square root of 2, where lambda is a real number. So I can't just put this down here because that's the gradient. Okay, cool. Now we want to find the tangent plane. So this one is also pretty straightforward, except now you kind of just do the dot product thing we saw from before. So you have that nabla phi of 2, 0, square root of 2 dot x minus 2, y minus 0, z minus square root of 2 is equal to 0, right? And you kind of just sub in everything from before. You have your 4, 0 minus 2 square root of 2 dot x minus 2, y minus 0, z minus square root of 2, and say that this is equal to 0. I trust that you guys can do the algebra. If you simplify this, this becomes 2x minus square root of 2z is equal to 2. And this is your tangent plane. Okay, so that's that section done. Moving on to Taylor polynomials. This section is probably a bit more straightforward. Right, so this stuff is, I think you've seen it before. Basically, what it says is that if you have fxy, this is equal to fyx, right? And we also used this before in our chain rule question, where we did the same thing. So that is basically what the mixed derivative theorem says. Okay, and yeah, before we go into the next section, if any of you guys forgot what the Hessian matrix is, that's what it looks like. And now moving on to our two-variable Taylor series. So basically we say that our two-variable Taylor series of xy around the point x0, y0 when satisfying the mixed derivative theorem is given by this one here. So this is basically very similar to, I guess, the stuff we saw from before, except now you have the Hessian matrix. And I guess this makes it a bit nicer because I guess it saves space, and then you can just easily expand it out after you find the Hessian. Okay, and now moving on to smooth and analytic functions. I'm not really sure how important this is for the exam. It probably won't be tested, but I think it would still be nice to go over it a little bit. Okay, so we have our definition. So say that omega is some subset of Rn, and that is some open set, right? And now you consider some function f that maps from omega all the way to Rn. So we say that f is of class c to the k if all partial derivatives of f up to order k exist and are continuous. So basically that means that your partial derivatives exist and are continuous at those points, right? So then we can say that the collection of all such functions is denoted by c to the k of omega. And we can write this as, I guess, the intersection of all of the c to the k of omega, which is basically what we call the collection of smooth functions on omega, right? Okay, and now moving on to analytic functions. If for all a, which is element of omega, there exists an open set UA, such that this limit here is true for all x, which is an element of UA, we say that f is analytic. So note here that the p here just kind of denotes the polynomial, so more specifically the kth order Taylor polynomial of f centered at a, right? So the collection of analytic functions on omega is basically denoted by this here. Okay, so note here, again, I'm not really sure how important this is for the exam, but it's good to know. If a function is analytic, then it's smooth. However, the converse is not necessarily true. And you can think about that yourself. Okay, and now moving on to our Taylor series question. So we want to consider some function f of xy and call it our cos of square root of x squared plus y squared. And now we want to find the Taylor series of f of xy at the point half 0 up to second order. So I'm not going to write this down because it's very, very computationally heavy. But basically, you can't just compute all the partial derivatives, right? So you have your f of half 0 is equal to pi 3, and you compute your partial derivatives all the way to second order, right? So you have your fx, fy, fxx, fyy, fxy, and of course from our previous theorems, this is just equal to fyx half 0, 0, right? So you don't have to do it again. Okay, so moving on, we then have our f of half plus hk, and we can just kind of sub it into our formula from before and write it as this. Note here that I kind of just expanded out the Hessian myself, so that's why it looks kind of a bit messy, right? And from here we can just substitute our values in. So after subbing everything in, you should get this expression here. So now we have that, and simplifying the expression, you get this. So from here, a trick you can do is to just let h to be equal to x minus half, and our k to be equal to y. So from here, we can just obtain our final form, which is this here. So yeah, this question isn't actually too hard, it's just very computationally heavy. Okay, so moving on to stationary points and extrema. So starting off with the definition of critical points, we have these three definitions. So we can consider f, which is some function, right? And we say that critical point of f is a point AB where nabla f is either 0 or does not exist, right? And then now we can also say that a stationary point of f is a point AB where nabla of f is 0. Okay, and then we also say that f has a local maximum minimum at AB if f of AB is the largest / smallest function value on some small disk centered at AB. So from there on, you can just kind of do a bunch of random stuff to determine the maximum minimum set of points, which is what I'm going to talk about here, right? Okay, so now we consider some element A, and that is in omega, which is a subset of Rn. We say that f, which maps from omega all the way to R, let it be a function. Then we say that A is a stationary point if nabla of f of A is equal to 0. And we also say that it is a global minimum if f of A is greater or equal to f of x, for all x is an element of omega. So this intuitively makes sense. Similarly, if you want it to be a global minimum, you have that f of A is or equal to f of x for all x is an element of omega. Okay, so now we have our local maximum, right? We say that it's a local maximum if there's an open set around A such that f of A is greater or equal to f of x for all x is an element of omega intersection A. And same thing applies for local minimum, except now the inequality sign kind of flips around, which makes sense, right? So now finally we have something called a saddle point. So what is a saddle point? A saddle point is a stationary point that is neither a maximum nor a minimum. Okay, and now we will learn how to classify such points. So moving on to our second derivative test, we have this very useful theorem, right? So we suppose that f maps from R2 to R, and that is a C1 function. So that means continuously differentiable function. And I suppose that nabla f of A is equal to 0. So what we can say is that if the determinant of the Hessian at A is less than 0, then A is a saddle point. Otherwise, if the determinant of the Hessian is greater than 0, then A is either a local minimum if fxx is greater than 0, and that A is a local maximum if fxx of A is less than 0. And unfortunately, if the determinant is equal to 0, then the test is not conclusive. So you'd have to, I guess, find the eigenvalues yourself to test it out. Okay, and now we're going to move on to the question of classifying stationary points, right? So let us consider f of xy is equal to x cubed minus 3x plus y cubed minus 3y. So our first step is to show that 1 minus 1 is a saddle point of f, right? And like all the previous questions, what do? We kind of just find nabla of f of xy. So we have that nabla of f of xy is equal to 3x squared minus 3, 3y squared minus 3, right? And since we've already computed nabla, might as well determine the Hessian as well, right? So our first component, we diff this with respect to x, so that becomes 6x. And the second component, you diff this with respect to y, so that becomes 0, right? And then same thing here. You have 0 and then 6y. So that's your nabla f of xy and Hessian done. Okay, and from here you can also kind of sub in your, actually let me just go on to the next slide. You can kind of just, actually I'll do it here. Okay, so we want to show that 1 minus 1 is a saddle point, right? So what you can do is you sub into nabla f of xy. So nabla f of 1 minus 1 is equal to 0, 0. So therefore we know that it's a stationary point. Now you kind of want to sub it into the Hessian. So when you sub it into the Hessian, you have this here, right? And from here you can calculate the determinant. So you have the determinant of hf of 1 minus 1 is equal to minus 26. And then you also have that. And because this is less than 0, you kind of don't really need to determine that fx is greater than 0. Because this is less than 0, then therefore it is a saddle point. Okay, and now moving on, we also want to classify the 3 other saddle points. So from before we have nabla f of xy is equal to 3x squared minus 3, 3y squared minus 3, which is equal to 0, 0, because they're stationary points. And from here you can say that the stationary points are 1, 1, minus 1, 1, minus 1, minus 1. And of course you also have your point from before, so your 1 minus 1, but I'm not going to classify this because you already classified it from before. Okay, so I'm also not going to do this case because it's very similar to the case from before. It's also a saddle point because the determinant is less than 0. So I'm just going to focus on these 2 instead, right? So for point 1, 1, you have that the Hessian at 1, 1 is equal to 6, 0, 0, 6, right? And the determinant of this is equal to 36, which is greater than 0. And you also have that fxx is equal to 6, which is greater than 0. So therefore this is a min. And now I'm going to do the point minus 1, minus 1. So of minus 1 is equal to minus 6, 0, 0, minus 6, right? If you compute the determinant, this is equal to 36, which is going 0. However, you know that fxx is equal to minus 6, which is less than 0. So this implies that it is a local max. And yeah, for the other point, so for the point minus 1, 1, I'll just leave that up to you because it's the exact same concept as the saddle point. Okay, and now moving on to critical points theorem. So now suppose that A is some element of Rn is a local max or min of a function, which maps from omega to R. Then we say that A is either a stationary point, or A is a boundary point, or F is not differentiable at A. And now we're gonna do this example, right? So we suppose that F maps from R2 to R, and is defined by fxy is equal to 4 minus x squared minus y squared multiplied by exponential to the minus x squared plus y squared. And from here, you kind of want to find other critical points. So one trick you can do here is to just let r squared to be equal to x squared plus y squared. So then it follows that fxy is equal to 4 minus r squared e to the minus r squared. Okay, and from here on, you once again just compute nabla. So nabla f of xy is equal to minus 2x, 5 minus r squared, e to the minus r squared. And at the bottom, you have minus 2y, 5 minus r squared, e to the minus r squared. Right, and we know that by the critical points theorem, this appears when nabla of f is equal to 0. Okay, so what we do now is we set nabla f to be equal to 0. So setting nabla f to be equal to 0, we get x multiplied by 5 minus r squared is equal to 0, and y multiplied by 5 minus r squared is equal to 0. So then this gives two cases, right? So if we have r squared is equal to 5, then x squared plus y squared is equal to 5. Otherwise, xy is equal to 0. So what can we say from this? We can say, therefore, the critical points are 0, 0, or xy, which is an element of r squared, such that x squared plus y squared is equal to 5. So this is just our circle with radius square root of 5. Okay, we're almost done. So recall that f of xy is equal to 4 minus r squared e to the minus r squared, right? So at 0, 0, we have that f of 0, 0 is equal to 4. So what this implies is that 0, 0 is the unique global maximum. Okay, that's done. And now we want to consider what happens when we are on the circle. So on x squared plus y squared is equal to 5, we have that f is equal to minus e to the minus 5. So every point on this circle is a global min. And also note that f of xy approaches 0 as the magnitude of xy approaches infinity. So therefore, no other extrema exists. sorry about that, it's like kind of stuck. Okay, so moving on, we have our extreme value theorem. So what we say is suppose that K, which is a subset of Rn, is compact, and that F maps from K all the way to R is continuous. Then we say that F attains a max and a min on K, that is, there exists AB, which is an element of K, such that for all X is an element of K, we can kind of squeeze F of X between F of A and F of B, right? And here's another example. So we are given some function f of xy, which is x squared plus y cubed minus 3y. And we consider another region U such that x squared plus y squared is less or equal to 16, x is less or equal to 0, and y is greater or equal to 0. So we want to explain why f attains a global max and min on U, and determine these extrema and where they occur. So for this, I kind of just typed that out, because again, it's just a bunch of computation stuff. So I guess the first thing you can know is that U is closed and bounded, so therefore it is compact. And since f is also a continuous function, by the extreme value theorem from previously, f attains a global max and min on U. So, like all of our previous questions, we can't just compute our nabla f of xy, which is equal to 2x 3y squared minus 3. And if we set our nabla f to equal to 0, we have that 2x is equal to 0, 3y squared minus 3 is equal to 0. And from here on, you can't just simplify everything. So from these two equations, you have the solutions x is equal to 0, y is equal to plus minus 1. So therefore, the critical point is 0, 1. And note here that 0, 0 and 0 minus 1 are not included, as they are not in the region. And you can check that yourself by looking at the bounds of U. Okay, and now we want to kind of parameterize the border of this region, right? So for C1, I've set it as T1, and T is bounded between minus square root of 15 to 0. And we also have our C2, which is from 0 to T, 0 to T, and T is bounded from 1 to 4. And for C3, because it's kind of just the curve along the arc, I set it as 4 cos theta, 4 sin theta. And of course, our theta is bounded between pi on 2 to pi minus arc sine 1 on 4. And you can kind of just draw it out to see what that looks like as well. So I think I'm just gonna draw up here. Yeah, so it looks something like that. And then, of course, it's a circle, so this length here is also 4. And if we call this theta, wait, sorry, not that. If we call this theta, then you can say that sine theta is equal to 1 on 4. So therefore, theta is equal to sine inverse of a quarter. And because you're going, I guess, from this way all the way to that way, you need to do the pi minus sine inverse of a quarter. So that's where I got the parameterization for the curve. Okay, so back to the question, if that would move. So on C1, we have g of t is equal to f of t1. So what I did here is I just kind of sub in t1 into the function. And from here, you kind of just do what you do in high school. You kind of just differentiate it and set it to equal to 0. So for here, t is equals 0 gives the stationary point. And if we sub it back into f, you get that the point is minus 2. And of course, we want to also check our endpoints. So g of minus square root of 15 is equal to 13. And now here that we don't check the other endpoint because we already determined it from before. Okay, and now for C2, very similar, except we set up kt to be equal to f of 0t. And subbing that in, you get t cubed minus 3t. If you differentiate the expression, you get 3t squared minus 3. Set it to be equal to 0, you have that t is equal to plus minus 1. However, t is equal to minus 1 is not a valid point, and you can check by the conditions above. And note here, we also don't need to check for t is equal to 1, as the point f of 0, 1 was already evaluated before. So what we do is we just check the remaining endpoint, right? So k of 4, if you sub it back in, you get that is equal to 52. Okay, and now for C3, very similar concept. Let's go scroll down. You sub in x is equal to 4 cos theta and y is equal to 4 sin theta into the curve. And you kind of just simplify the whole thing and call it h of theta, right? So you get 16 cos squared theta plus 64 sin cubed theta minus 12 sin theta. If you differentiate that and equate it to be equal to 0, you can also solve for the expression. So from the expression, you get that either cos theta is equal to 0 or 192 sin squared theta minus 32 sin theta minus 12 is equal to 0. And just use your quadratic formula, sub everything in, and you should get this answer here. And of course, you kind of just sub that expression back into your function h from before. And you can kind of just use your Pythagorean identity for trig to find what causes. So the number's not very nice, but you end up getting 403 minus 20 square root of 10 on 27. Okay, and now you're pretty much done. You just want to compare all the points. You have your min f is at minus 2 at 0, 1, and your max f is equal to 52 at 0, 4. Okay, so now moving on to Lagrange multipliers. So we consider function f and function phi, which are differentiable, and we consider s, where x is an element of Rn, such that phi of x is equal to c. And this defines a smooth surface on Rn. So we say that if f attains a local maximum or minimum at a point A, then nabla f of A and nabla phi of A are parallel. So then if you solve this equation, you can essentially find the points. Okay, and now to our next question. So we have this rectangular box, which has 3 faces on the coordinate planes and opposite vertex x, y, z constrained to lie on the surface. Z is equal to f of x, y, right? So let's consider some function f, which is C2, so twice continuously differentiable, and make it strictly concave, right? We want to show that any maximizer satisfies this condition here. So from here, you kind of just use your Lagrange multipliers you saw from before. Just gonna scroll down a bit. You have, so what you can do is say that the following is obtained by the product of x, y, z, right? And now we want to constrain it to phi x, y, z is equal to z minus f of x, y is equal to 0. So now we can kind of just use our Lagrange multipliers, right? Can say that yz, xz, xy is equal to lambda minus fx minus fy 1. So for this, I just did with respect to x, and then this with respect to y, this with with respect to z. And for here, same thing. So now you can kind of try to determine some expression for fx and fy. One way to go about this is to, I guess, first write it like this. So you have that yz is equal to minus lambda fx, xz is equal to minus lambda fy, xy is equal to lambda. And then if you equate all the lambdas together, you can say that minus yz on fx is equal to minus xz on fy, which is equal to xy. So from here on, you can just rearrange everything. You have that your z is equal to minus x fx, which is equal to minus y fy. So therefore, your fx is equal to minus z on x, fy is equal to minus z on y. And you have your nabla f is equal to minus z on x, minus z on y. And because our z is just f of xy, this satisfies this. Yeah. Okay, and now for another question, we're moving on to Lagrange multipliers. Okay, so let A to be a symmetric matrix, and we're going to define our f of V to be V transpose AV, where V is an element of Rn. And now we also want to consider some disk, so let's call it D. And we want to constrain it such that the magnitude of the vector V is always less or equal to 1. Okay, so we want to show that any non-zero vector at which a non-zero extremum is attained must lie on the boundary magnitude of V is equal to 1. And what can you really say about these points, right? So the first thing you can say is that D is closed and bounded, is compact, and f of V is continuous. So by extreme value theorem, f attains a maximum and minimum on D. Let me remove that. Okay, and now we have our case 1. So I guess the first one we can consider is the interior. So on an interior extremum, our nabla f of V is just equal to 2AV. And we set that to be 0. So we know that this is true when V is an element of the kernel of A. And this is the interior critical point. And if we sum it back into FV, you get that this is equal to 0. However, this does not satisfy the condition given by the question, because it says that we want to show any non-zero vector at which a non-zero extremum is attained, but this is not non-zero, right? So now we move on to case 2 and look at the boundary. Okay, so using Lagrange multipliers and a constraint, g of V is equal to V transpose V minus 1 is equal to 0. We say that nabla F is equal to lambda nabla G implies that 2AV is equal to 2 lambda V. So then it follows that AV lambda V is AV is equal to lambda V. So therefore our extreme occur at eigenvectors of A. Okay, and now for an additional question. We want to show that the maximum and minimum values of V transpose AV of all unit vectors are the largest and smallest eigenvalues of A respectively, right? So if we kind of just use what we derived from before, you can say that f of V is equal to V transpose AV, and that this is equal to lambda magnitude of V squared. And because V is a unit vector, that's just equal to 1. So simplifying that, you just get lambda. So therefore the maximum value is lambda max and the minimum value is lambda min. Okay, final topic, our inverse and implicit function theorems, if that would scroll down. Okay, so starting off with the inverse function theorem, we suppose we have some region omega which is open, and that A is an element of omega, and that F maps from omega to Rn is a C1 function. So if our Jacobian of Fa is an invertible matrix, then we can say that F has a local inverse around A, right? So what that means is that we can obtain, there are basically open sets U and V and a function G such that these identity functions hold. So moreover, we can also say that G is some continuously differentiable function such that this holds as well. And you can imagine that you can also do some affine approximation stuff using this. Okay, so for this example, let F map from AB to CD and say it is a bijection. And let's say that F is also differentiable with F dash of X is not equal to 0 for all X is an element of AB. Then F inverse is differentiable everywhere, right? And we want to show that if F is an element of C2AB, then that is true. Okay, so for this question, you kind of just sub all the points into the theorem from before. So let G to be your inverse function. And we know that since F is bijective and F dash of X is not equal to 0, the inverse function theorem gives that result. And now you just kind of want to differentiate it again and use the chain rule. So you get that expression there. So differentiate both with respect to y, you get this very messy expression. However, you know that g dash of y is equal to 1 on f dash of g of y. So if you sub it in, you get that this is true. And since f is a twice continuously function, a to b, both f dash and f dash dash are continuous. And since g is equal to f inverse is continuous, it follows that g dash dash of y is also continuous. So you say that, therefore, f inverse, which is an element of C to CD, is f inverse is an element of C to CD. Okay, and now moving on to our next question. Okay, so let's just consider some function f that maps from R2 to R2 be given by f of xy is equal to x squared plus x plus 2y, x squared plus 3y. And from here, you kind of just want to find the Jacobian matrix. So for part I, you say that the Jacobian matrix f is just equal to 2x plus 1, 2x, and 2, 3. So first column, I just differentiated it with respect to x, and second column with respect to y. Okay, and now you can't sub in the points. So j0, 0, f is equal to 1, 2, 0, 3. Right, and from here you can say that the determinant is equal to 3, which is not equal to 0. And since f is an element of C1, we can say that by the inverse function theorem, f has a differentiable inverse around 0, 0. Okay, so that's kind of the inverse function theorem done. And if you want to find an affine approximation, you can also do so using that. Okay, and now moving on to the implicit function theorem special case. So for the special case, we are considering phi, which is a function that maps from Rm plus 1 to R, and that would be a C1 function, and we want to express an element of Rm plus 1 as this vector here. So we say that AB, which is an element of Rm plus 1, satisfies phi of AB is equal to 0. And we say that the partial diff with respect to Z is not equal to 0. Then there exists some open sets U and V, and a continuously differentiable function f that maps from U to V, such that these conditions are satisfied. Okay, and now for a question that uses this case of implicit function theorem. So let's consider some function f and say that is equal to x sine z minus y cos z. And we want to define the helicoid surface such that S is equal to xyz, which is an element of R3, such that f of xyz is equal to 0. So from here, we want to fix a point, x0, y0, z0, which is an element of S, with x0, y0 is not equal to 0. And the rest is just pretty much just using implicit function theorem, right? We want to show there exists an open neighborhood of x0, y0 with a smooth function such that f is equal to 0 for all x, y is an element of U. So you know that x0, y0, z0 is on the surface, so you can just sub those points in. And now computing the partial derivative of f with respect to z, you have that, and because x0, y0, z0 is on the surface, you can also just sub that in, right? So for this here, you kind of just do proof by contradiction. You suppose that the negation is true. So if we suppose the partial diff with respect to z is equal to 0, then the sum of, let's call this equation 1, and let's call this equation 2. 1 squared plus 2 squared is equal to 0, right? If you expand this out, you will get that x0 squared plus y0 squared is equal to 0. However, this only occurs when x0 is equal to y0 is equal to 0. So this is a contradiction, so therefore this is never true. So therefore our initial statement is false. And this is just kind of your bread and butter sort of thing. You kind of just put this at the end of your proof. If that would scroll up. Okay, and now moving on to the notes. So basically, although our theorem guarantees that f of x, y, z is equal to 0 can be solved locally for z as a smooth function of x, y, there does not exist a continuous function such that that is true. So using polar coordinates, we can allow x to be equal to r cos theta and our y to be r sine theta. So if we sub that in and using our trig compound angles, we can express that as r sine of z minus theta. So the condition becomes sine of f of xy minus theta is equal to 0. And this is only true when f of xy is equal to theta plus k pi. And I'll add here that k must be an integer. So from here on, you can kind of just fix your r is equal to 1 and define some function gamma of t and call it cos t sine t, where t is an element from 0 to 2 pi. So if we set g of t to be some function in terms of cos t and sine t, it follows that g of t is equal to t plus k pi, where k is an integer. And note here that g of t is continuous because f is continuous. Okay, so we now know that gamma of 0 is equal to gamma of 2 pi. So the continuity of f implies that g of 0 is equal to g of 2 pi. And it follows that k pi is equal to 2 pi plus k pi. If you subtract k pi from both sides, you have that 2 pi is equal to 0. However, this is a contradiction. So in other words, we can say that the helicoid cannot be written globally as a single continuous function over the punctured plane. Okay, and now for the more general case of the implicit function theorem. This is kind of similar to the one from before, except now your phi is mapping from r to the n plus n to Rn. So let that be a continuously differentiable function, and we will write our xy as before as some vector for an element of r to the n plus n. Okay, and let a b to be an element of r n plus n satisfy phi of ab is equal to 0, and consider that this is true. And I think that's a typo, it should be n. We say that if the partial diff is invertible, then there are open sets U subset of Rm and phi subset of Rn, and a surjective function f such that these conditions hold. And we have that phi of xy is equal to 0 if and only if f of x is equal to y. Okay, and now we want to do a question on the more general case of the implicit function theorem. So for question 1, we want to find one point which satisfies the system, and that on some neighborhood of this point, there is some C1 function f with uv, f of xy, and we want to justify f naming any theorems. Okay, so for this, I determined the point to be pi 0 log pi 0, and I set the function phi to be equal to x minus e to the u cos phi, phi minus e to the y sine x. So it follows that if you compute the partial derivative with respect to uv, you get this here. And from here, you can just sub in the points. So you sub in pi 0 log pi 0 into the matrix from before, and you compute the determinant, and because it is not equal to 0, it means that the matrix is invertible. And since phi is a continuously differentiable function, by the implicit function theorem, the result holds. So now for part 2, we want to compute the determinant of the Jacobian and show that it is equal to phi on x. Okay, so this is basically just an application of chain rule, right? You differentiate that in the xy direction and then in the uv direction, and you just chain rule it. And of course, this is just equal to 0. And now you can't just rearrange the equation and you get this. And from here, you can kind of just compute the determinant. So the determinant of this, you just take the reciprocal. And this minus 1, because it's technically just like a 2 by 2 matrix, minus 1 all squared is equal to 1. So that's why this expression here, you don't have the minus 1 anymore. And this is just a bunch of computational stuff. This is just obtaining the Jacobian matrix with respect to xy and the Jacobian matrix with respect to uv. And you kind of just compute the determinant of them and sub it in to the expression from before. And you get that this is equal to phi on x. Okay, now we want to find the best affine approximation. So recall that the best affine approximation is given by this expression here. And from here, you can just kind of use your implicit differentiation. So differentiate with respect to x, we're just going to do that to both equations. So for the first line, if you differentiate with respect to x, the first component just becomes 1. But the second component, because none of it is in terms of x, you kind of have to just use your implicit differentiation here, which is basically just your chain rule, right? And the same thing for the second equation. you have Vx, so you're differentiating with respect to x. And then because you have your sin x here, you want to put that out. So that is equal to 0. And evaluating at pi 0, ln pi 0, you have that ux is equal to 1 on pi and vx is equal to minus 1. And the same thing, differentiating with respect to y, just implicit differentiation again. So you get these two equations. Okay, and evaluating at pi 0, ln pi 0, you get that both of them are equal to 0. Okay, so now you have your ux, vx, uy, vy. You can just kind of put it into your matrix. Yeah, so basically just solving it all into your affine approximation from before. You can just kind of expand everything out, and you should be able to get this expression here. If that would go down. Yeah, there we go. Yeah, and that's the end. I mean, there's like a slide afterwards. Okay, there we go.